Look up at the night sky, at that vast ocean of darkness punctuated by points of light. It's a sight that has captivated us for millennia, but what we see is only part of the story. For billions of years after the Big Bang, the universe was a far simpler and in many ways a far emptier place. It was a cosmic soup, a thin, hot broth of the most basic ingredients: hydrogen, a little helium, and trace amounts of lithium. Just simple atoms drifting in an immense and silent darkness. There were no planets, no stars as we know them, and certainly no life. The universe, for almost all of its early existence, was fundamentally boring. But then something incredible happened. In the cold, dense clouds of gas that would eventually collapse to form the first stars, a quiet revolution began. The universe, almost as if by a secret recipe, started to cook. Simple atoms began to link together, forging the very first complex molecules in the history of everything. This was the moment the cosmos became interesting, the moment the stage was set for everything that was to come. This transition from a barren cosmos of simple atoms to one capable of building complexity is one of the greatest unsolved mysteries in all of science. How did the universe go from utter simplicity to the breathtaking chemical diversity we see today? How did it assemble the first molecular building blocks, the potential precursors to life itself, in an environment that was seemingly hostile to such delicate structures? This isn't just a question for chemists or astronomers, it's a question that lies at the very heart of our own existence. The molecules that eventually led to planets, to oceans, and to us had to start somewhere. Their origin story is our origin story, written in the faint chemical signatures of ancient gas clouds and the violent births of the first stars. In this video, we are going on a journey to that cosmic dawn. We will explore 30 of the most fascinating, compelling, and sometimes downright strange scientific theories about how the universe's first complex molecules came to be. We'll venture into the hearts of protostellar nebulae, ride the shockwaves of supernova explosions, and even consider the possibility that the crucial ingredients for complexity arrived on tiny grains of interstellar dust. This is a detective story on a universal scale, and each theory is a piece of evidence, a clue left behind from the earliest chapters of cosmic history. So get ready to dive into the wild and wonderful ideas that scientists are investigating right now, as we attempt to unravel the mystery of how a simple universe learned to build, and in doing so, set in motion the chain of events that led eventually to you. Our journey begins not with a bang, but with a slow, patient simmer in the coldest, darkest places imaginable. Far from the violent infernos of stars, in the vast and silent spaces between them lie immense, frigid clouds of gas and dust. These are the molecular clouds, the nurseries of future stars, and according to our first theory, they were also the universe's first chemistry labs. This is the idea of a primordial soup in deep space, a concept that suggests complexity arose from simplicity in the quietest corners of the cosmos. To understand why these clouds are so special, picture the early universe we just described. It was a hot, diffuse plasma where atoms, buzzing with immense energy, would smash into each other and immediately fly apart. There was no chance for delicate chemical bonds to form. But as the universe expanded and cooled, matter began to clump together. In regions that were slightly denser, gravity pulled atoms closer, forming these massive, cold clouds. The temperature inside them can plummet to just 10 degrees above absolute zero, creating an environment where atoms and molecules move incredibly slowly. This slowness is the first crucial ingredient. It means that when two atoms happen to meet, they don't just bounce off each other with violent energy. They have a chance to linger, to interact, and perhaps to stick together. But simply being cold and slow isn't enough. You need a surface, a meeting place. This is where a seemingly insignificant component of these clouds plays a starring role: interstellar dust grains. These are tiny particles smaller than a wavelength of light made of silicates or carbon. They are the cosmic catalysts. Imagine them as microscopic dance floors adrift in the void. Individual atoms like hydrogen, carbon, oxygen, and nitrogen drifting through the cloud eventually bump into these dust grains and stick to their surfaces. Now, instead of having to find each other in the immense emptiness of space, these atoms are held in close proximity on a solid surface. They can slide around, meet other atoms, and under the right conditions form bonds. A hydrogen atom might link with an oxygen atom to form a hydroxyl radical. Carbon and oxygen can form carbon monoxide. This process, known as surface chemistry, is thought to be the primary way simple molecules like molecular hydrogen formed in the early universe, and it's the foundation for building even more complex structures. Of course, chemistry requires energy. You can't just have frozen atoms sitting on a dust grain. You need a little spark to initiate the reactions. But in these clouds, too much energy would be disastrous, shattering the fragile bonds as soon as they form. So where does this precise, gentle energy come from? The theory points to two cosmic sources. The first is the faint, pervasive glow of starlight from distant stars, which can provide just enough photons to nudge atoms into reacting without tearing them apart. The second, perhaps counterintuitively, is cosmic rays. These are high-energy particles racing across the galaxy. When one slams into a dust grain, it can deposit a tiny, localized burst of energy, heating the grain for a fraction of a second. This brief warm-up can give the atoms on the surface the activation energy they need to jump into a new configuration, forming a more stable, complex molecule before the grain cools back down. The most compelling evidence for this theory doesn't come from telescopes pointed at distant clouds, but from rocks that have fallen to Earth. We have found carbon-rich meteorites, chunks of asteroids that are remnants from the solar system's formation, which contain a rich inventory of organic molecules. Most significantly, scientists have detected amino acids like glycine within them. Amino acids are the fundamental building blocks of proteins, essential for life as we know it. The fact that these complex molecules are found in material that is billions of years old strongly suggests that the chemical processes happening right now in molecular clouds are not new. They are a fundamental part of the universe's operating system, a slow, continuous cooking process that has been enriching the cosmos with chemical complexity since long before our sun was even a twinkle in a galactic cloud. This theory paints a picture of a universe that is inherently fertile, where the seeds of future complexity are woven into the fabric of space itself. But while the deep, cold clouds of space were patiently assembling simple molecules, another, far more dramatic process was unfolding much closer to home. This second theory shifts our focus from the vast interstellar medium to the chaotic construction zone of our own early solar system. It proposes that some of the most crucial molecular building blocks weren't just formed in space, but were forged and then delivered to our planet by celestial messengers, comets and asteroids. This idea transforms these objects from mere rocky or icy wanderers into key players in the story of life's origins, acting as both factories and freight trains for organic chemistry. To understand how they could serve as chemical factories, we need to look at their composition, especially that of comets. Often called dirty snowballs, comets are cosmic time capsules, preserving material that has remained largely unchanged since the solar system's birth. Their nuclei are a mixture of ices, primarily water ice, but also frozen gases like methane, ammonia, and carbon monoxide, all embedded with dark, dusty organic material. This frozen reservoir becomes a potent chemistry set when subjected to energy. As a comet journeys from the outer solar system on its elliptical orbit towards the Sun, two powerful energy sources begin to work on it. The first is ultraviolet radiation from the Sun. Even in the cold depths of space, this relentless UV light can break apart the simple molecules in the comet's icy crust, creating highly reactive fragments known as radicals. These radicals, now desperate to form new bonds, can recombine into more complex organic molecules right there on the surface. The second, more intense energy source is heat. As a comet approaches the Sun, its surface ices begin to sublimate, turning directly from solid to gas, creating the spectacular comas and tails we see from Earth. This process isn't just a light show, it's a profound chemical transformation. The warming ice creates a liquid-like layer around the dust grains, a temporary environment where molecules dissolved in water can mingle and react, potentially forming even more complex structures like amino acids and nucleobases. For a brief period, a comet can become a miniature, mobile chemistry lab, with conditions that mimic the warm little ponds once theorized to be the cradle of life on Earth. The real power of this theory, however, lies in the delivery. The early solar system was a violent shooting gallery, a period known as the Late Heavy Bombardment, where countless comets and asteroids rained down upon the inner planets. This wasn't just destruction, it was a cosmic seeding event. Each impactor that struck the young Earth was a cargo ship loaded with pre-formed organic compounds. While the impact itself was cataclysmic, scientists believe that some comets, especially smaller ones or those hitting at a shallow angle, could have fragmented in the atmosphere, gently scattering their organic-rich debris across the planet's surface. This would have deposited a rich supply of life's potential ingredients directly into the primordial oceans and lakes, providing a foundational stockpile of complex molecules that would have taken much longer to form from scratch on Earth alone. We no longer have to rely solely on theory for this. We have gone to see for ourselves. The European Space Agency's Rosetta mission provided stunning confirmation. For 2 years, the Rosetta spacecraft orbited comet 67P/Churyumov-Gerasimenko, and its lander, Philae, actually touched down on the surface. The data sent back was a revelation. Rosetta didn't just find simple ices, it detected a stunningly diverse cocktail of organic molecules in the comet's coma, including the amino acid glycine and key components of DNA and RNA like phosphorus. This direct evidence confirmed that the chemistry within these icy bodies is sophisticated enough to produce the very molecules that are fundamental to biochemistry. It powerfully supports the idea that comets could have played a critical role in jump-starting the journey toward life by showering a sterile Earth with the essential Lego blocks of biology. Yet for all the promise of these cosmic delivery systems, there is another compelling possibility, one that looks not to the heavens but to the deepest, darkest parts of our own planet. Our third theory suggests that the stage for the universe's greatest chemical breakthrough was not a frigid interstellar cloud or a frozen comet, but a scalding, mineral-rich cauldron at the bottom of the ancient ocean. This is the theory of hydrothermal vent synthesis, an idea that places the origin of life's building blocks in the extreme environments of deep-sea vents on the early Earth. Imagine the young Earth, a turbulent world still cooling from its violent formation. Its surface is a molten hellscape bombarded by asteroids with an atmosphere toxic to life as we know it. But beneath the waves, a different kind of drama was unfolding. Along the mid-ocean ridges where tectonic plates were pulling apart, the planet's immense internal heat was venting into the cold, deep ocean. These weren't gentle hot springs, they were monumental structures often called black smokers, spewing superheated water, rich in dissolved minerals like iron, sulfur, and nickel from the Earth's crust. This created an environment of staggering contrasts, where water heated to hundreds of degrees Celsius met the near-freezing ocean depths. It is within this chaotic interface of heat, chemistry, and geology that this theory finds its power. The magic of these vents lies not just in the heat, but in the intricate structures they build. As the mineral-rich, superheated water jets out and mixes with the cold seawater, the dissolved minerals rapidly precipitate, building tall, porous chimney structures. These chimneys are far more than just geological curiosities. They are believed to have acted as the planet's first natural laboratories. Their porous, honeycombed interiors create a massive surface area, a labyrinth of microscopic nooks and crannies. Within these tiny chambers, simple molecules like carbon dioxide, hydrogen, and ammonia, which would have been abundant in the vent fluids and the early ocean, could become concentrated. This concentration is a critical first step, increasing the chances that these molecules would collide and react. But the vents provide more than just a meeting place. They offer a continuous and reliable source of energy. The theory posits that the key driver for chemistry here wasn't sunlight or cosmic rays, but a persistent energy gradient. The vast difference in temperature and chemical composition between the hot, acidic vent fluid and the cold, alkaline ocean water creates a natural flow of energy not unlike a battery. This gradient could have been harnessed to fuel chemical reactions that build complexity, moving molecules from a state of low organization to high organization. The mineral surfaces of the vent chimneys, particularly those rich in iron and sulfur, are also excellent catalysts. They can lower the energy required for reactions to occur, guiding simple molecules to form more complex organic compounds, perhaps even the precursors to amino acids and lipids. What makes this theory so compelling to many scientists is that it provides a plausible bridge from mere chemistry to the edge of biology, all within a protected setting. The deep ocean would have offered a sanctuary from the hostile surface conditions of the early Earth, shielding fragile emerging molecules from destructive ultraviolet radiation and asteroid impact. Furthermore, the microscopic pores in the vent structures could have acted as primitive cell membranes, compartmentalizing the newly formed molecules and allowing them to interact in a confined space. This could have led to the formation of self-sustaining chemical cycles, a crucial step toward the emergence of life. The vent environment, with its steady supply of energy and raw materials, its catalytic surfaces, and its protective compartments, presents a comprehensive package that elegantly addresses many of the challenges of abiogenesis, suggesting that life may not have been a lucky accident in a quiet pond, but an inevitable consequence of our geologically active planet's energetic chemistry. While the deep sea vents offered a turbulent, energy-rich cradle, another compelling theory suggests the first steps toward complexity occurred in a far more orderly environment on the shores of the young Earth's primordial seas. This idea focuses on the remarkable properties of seemingly mundane materials, clay minerals. Far from being just dirt, certain types of clay are now thought to have acted as nature's first laboratories, providing both a scaffold and a catalyst to assemble the universe's first complex organic molecules right here on our planet. The power of this theory lies in the unique molecular architecture of clays like montmorillonite. Picture the structure of clay under a powerful microscope. It isn't a solid lump. Instead, it's made up of countless tiny, stacked layers like pages in a book. These layers carry a slight electrical charge, creating a surface that is incredibly attractive to other molecules. In the nutrient-rich soups of the early Earth's ponds or shallow coastal waters, simple organic building blocks, things like nucleotides, the individual letters that make up RNA, and amino acids, would have been drifting freely. The charged surfaces of clay particles would have acted like molecular magnets, pulling these drifting compounds out of the dilute solution and concentrating them into a much denser, more reactive film on their surfaces. This act of concentration is a critical first step. It dramatically increases the chances that these molecules will bump into each other and react, overcoming the problem of dilution that would have made assembly in the open ocean nearly impossible. But clays offer more than just a sticky meeting place. Their surfaces are not chaotic. They possess beautifully regular, repeating patterns of atoms and charges. This order is thought to have played a guiding role, a kind of molecular template, As nucleotides, for example, gathered on the clay surface, these patterns could have helped align them in a specific orientation, positioning them just right so that chemical bonds could form between them. Instead of a random, messy tangle, the clay surface encourages a structured assembly line. Experiments have shown that montmorillonite clay is particularly effective at catalyzing the formation of chains of RNA from individual nucleotides. RNA is a molecule of profound importance, as it can not only store genetic information like DNA, but also catalyze chemical reactions, leading to the RNA world hypothesis, which suggests RNA was the first self-replicating molecule of life. The clay, in this scenario, acts as a non-biological predecessor, a stage manager that orchestrates the formation of the first actors in the play of life. This theory elegantly bridges the gap between the non-living world of geology and the emerging world of biochemistry. It suggests that the transition from simple chemistry to the threshold of biology wasn't a fantastically unlikely event, but a natural consequence of the physical and chemical properties of common Earth materials. The clay minerals themselves would have been abundant on the early Earth, formed by the weathering of volcanic rocks. They provide a stable, protected environment, much like the pores of hydrothermal vents, shielding delicate emerging molecules from degradation by ultraviolet light. What's especially elegant is that once these first RNA chains grew to a certain length on the clay surface, they could have been released, perhaps by changes in water salinity or pH, setting them free to explore their newfound catalytic capabilities in the surrounding environment. This vision of life's origins is one of patient molecular-scale construction, where the very ground beneath our feet may have provided the architectural plans for the first complex structures that would eventually lead to the rich tapestry of life. But moving from the organized surfaces of clay minerals to a truly self-replicating system requires a molecule of almost magical versatility. This brings us to one of the most profound and influential ideas in the study of life's origins, the RNA world hypothesis. This theory proposes that before the elegant division of labor we see in modern biology, where DNA stores information and proteins do the work, there was a much simpler era dominated by a single, multi-talented molecule, RNA. In this ancient world, RNA would have been the star player, acting as both the genetic blueprint and the chemical catalyst, a molecule capable of copying itself and kickstarting the journey toward life. The appeal of RNA is clear when you break down its dual capabilities. Like its more famous cousin DNA, RNA is a nucleic acid, a chain made from building blocks called nucleotides. Each nucleotide consists of three parts: a sugar, a phosphate group, and a nucleobase. The sequence of these nucleobases, adenine, guanine, cytosine, and uracil, can carry information, a genetic code just like DNA. But unlike the relatively stable and passive DNA, RNA is a much more dynamic and structurally versatile molecule. It can fold into intricate three-dimensional shapes, and some of these shapes can act as enzymes, speeding up specific chemical reactions. We see evidence of this today in our own cells with ribosomes, the machines that build proteins being powered by ribosomal RNA, not a protein enzyme. This suggests that RNA is perfectly capable of performing the complex chemical work needed for a primitive life form to function. The grand vision of the RNA world, however, runs into a monumental challenge when we try to explain its very first steps. How could such a sophisticated molecule possibly assemble itself from scratch on the early Earth? The hurdle is not just making the individual ingredients, but also linking them together reliably. Let's consider each component. The nucleobases, like adenine and guanine, have been shown to form under conditions that mimic the early Earth's atmosphere or hydrothermal vents, which is promising. The phosphate needed for the backbone is also geologically plausible, but the sugar in RNA, ribose, is a major stumbling block. In laboratory experiments that simulate prebiotic chemistry, when you try to form sugars from simple precursors like formaldehyde, you don't get a nice, clean batch of ribose. Instead, you get a messy tar of many different sugars, and ribose is notoriously unstable, breaking down quickly in the conditions that likely existed on the young planet. Getting enough pure, stable ribose to build long RNA chains seems incredibly difficult, and even if, by some fortunate circumstance, a pool of nucleotides manage to form, the next challenge is just as daunting: polymerization. How do you string these individual nucleotides together into a long, information-carrying chain? Water is the enemy of this reaction. It constantly tries to break the bonds apart. On clay minerals or at hydrothermal vents, you might get short chains, perhaps 10 or 20 units long, but a molecule needs to be much longer to fold into a useful shape and perform a catalytic function. Creating an RNA molecule long enough to be a self-replicator from a random soup of chemicals starts to seem like a miracle. This has led many scientists to propose a compelling solution. The RNA world probably wasn't the very first world. Instead, it was likely preceded by a pre-RNA world, where much simpler, more robust molecules acted as the first genetic systems. These alternative molecules could have served as stepping stones, fulfilling the basic role of information storage and replication without all the fussy chemical requirements of RNA. Imagine molecules like peptide nucleic acid, or PNA, where the sugar phosphate backbone of RNA is replaced by a more stable peptide-based structure. PNA can still base pair with itself, meaning it can carry information in a sequence, and it's far less prone to degradation. Another candidate is threose nucleic acid, TNA, which uses a different, potentially easier to form sugar. These simpler molecules could have emerged more readily from the prebiotic soup, establishing the fundamental principle of molecular replication. Over vast stretches of time, through a process of chemical evolution, this primitive system could have gradually refined itself, eventually transitioning to the more versatile, though more complex, RNA. This stepping stone hypothesis doesn't solve all the problems, but it makes the emergence of the RNA world feel less like a single, impossible event and more like a plausible, stepwise evolutionary process where chemistry slowly and patiently laid the groundwork for biology. While clay minerals and deep-sea vents offered grounded laboratories for chemistry, another theory suggests the recipe for life's first ingredients was written in the sky itself. This idea turns our gaze upward to the very air that surrounded the young Earth, proposing that our planet's primitive atmosphere acted as a colossal, planet-scale photochemical reactor. In this scenario, the key ingredient wasn't a mineral surface or a thermal gradient, but the raw, unfiltered energy of our sun, which broke apart simple gases and reassembled them into something far more interesting. To set the stage for this atmospheric alchemy, we need to imagine an Earth with a fundamentally different air supply. Billions of years ago, our atmosphere was likely a reducing one, meaning it was rich in gases like methane, ammonia, hydrogen, and water vapor, but crucially, it lacked free oxygen. This chemical composition is vital because oxygen is highly reactive. It tends to break down complex organic molecules, effectively sterilizing the environment. An oxygen-free atmosphere, however, would have been a fertile ground for building molecules, not tearing them apart. More importantly, without oxygen, there was no ozone layer. Today, the ozone layer high in our stratosphere acts as a planetary sunscreen, absorbing the sun's most energetic ultraviolet radiation. On the early Earth, this protective shield was absent, allowing the full, blistering intensity of UV light to pour down onto the upper atmosphere. This intense ultraviolet radiation is the engine of the theory. As these high-energy photons slammed into molecules of methane and ammonia in the upper atmosphere, they didn't just warm the air, they acted like tiny cosmic sledgehammers, delivering enough energy to shatter the chemical bonds holding these simple molecules together. This created a soup of highly reactive fragments, methyl radicals, hydrogen atoms, amino radicals, and more. These fragments, desperate to regain stability, would then collide with each other and with other molecules in a frenetic dance of recombination. And in this chaotic process, the simple building blocks could reassemble into more complex organic compounds. Think of it like breaking a handful of simple Lego structures into individual bricks by shaking them violently, then allowing them to randomly snap back together. While most new structures will be just as simple, a few, by pure chance, will form more elaborate and interesting shapes. In the atmosphere, this could have produced molecules like formaldehyde, hydrogen cyanide, and other precursors to the building blocks of life. The most famous support for this idea comes not from a telescope, but from a glass apparatus in a laboratory in 1953. Chemists Stanley Miller and Harold Urey designed a now legendary experiment to test this very hypothesis. They created a closed system that mimicked the presumed conditions of the early Earth. They filled one flask with water to represent the ocean, and another with a mixture of methane, ammonia, and hydrogen to represent the atmosphere. They then passed electrical sparks through the gaseous mixture to simulate lightning, another potent energy source, and condensed the resulting products back into the water flask, creating a cycle akin to rain. After just 1 week, the results were astounding. The previously clear water had turned a murky brown, and upon analysis, it was found to contain several different amino acids, the very molecules that form the proteins essential for life. The Miller-Urey experiment was a watershed moment, proving for the first time that the basic ingredients of biology could arise from simple, non-biological starting materials under conditions that could plausibly have existed on the early Earth. Of course, our understanding of the early atmosphere has evolved since the 1950s, and many scientists now believe it was less reducing than Miller and Urey assumed, potentially containing more carbon dioxide and nitrogen. When the experiment is repeated with these updated gas mixtures, the yield of amino acids is lower, but it doesn't drop to zero. Significant organic molecules still form, especially when other energy sources like ultraviolet light, which is now considered even more important than lightning for this process, are used in the simulation. Furthermore, the theory gains strength when we consider the sheer scale and duration of the process. This wasn't a small lab experiment running for a week. It was a global phenomenon operating continuously for millions of years. Even a low, steady rain of organic molecules from the skies, accumulating in the ancient oceans and lakes, could have created a significant concentration over geological time, providing a rich reservoir of potential for the next steps in life's origin story. This vision of a young Earth being gently seeded with the stuff of life from its own skies presents a powerful and elegant picture of a planet actively participating in its own journey toward complexity. Now let's venture back into the deep freeze of space, but with a surprising new perspective. We often think of extreme cold as a state of inactivity, a pause in molecular motion. But when it comes to building complexity in the near-total vacuum of space, this profound cold might have been the universe's greatest ally. This theory posits that the icy hearts of molecular clouds, chilling at just 10 to 50 degrees above absolute zero, were not a chemical dead end, but a perfectly calibrated environment for a special kind of quantum-assisted chemistry to unfold. The logic seems counterintuitive at first. In a warm environment, molecules zip around with high energy, colliding frequently. This is great for some reactions, but it's disastrous for building delicate, complex structures. A fragile, newly formed bond would be shattered by the next energetic collision. In the extreme cold of a molecular cloud, however, everything slows to a crawl. Atoms and molecules have very little thermal energy, moving with a lethargic slowness. This lack of violent motion is the first key advantage. It means that when a chemical bond does manage to form on the surface of a dust grain, it's unlikely to be broken by a random jostle from a neighbor. The cold provides a state of stability, a quiet workshop where intricate structures can be assembled without constant interruption. But if everything is so slow, how do reactions happen at all? This is where the magic of quantum mechanics enters the picture. For a reaction to occur, two particles need to overcome an energy barrier, like rolling a ball over a hill. In our everyday world, a molecule gets the energy to climb this hill from heat. In the deep cold of a molecular cloud, there simply isn't enough heat for this to happen at any significant rate. Yet we observe complex molecules there. The solution is a bizarre quantum effect called tunneling. Imagine that energy barrier is not a hill but a solid wall. Classical physics says the ball can't get through. Quantum mechanics, however, allows for a fascinating possibility. There's a small, probabilistic chance that the ball could simply appear on the other side of the wall without ever going over the top. It's as if it tunnels through. In chemical terms, this means that atoms, particularly the tiny and quantum mechanically fuzzy hydrogen atom, can sometimes bypass the traditional energy barrier and bond with another molecule, even when they are technically too cold to do so. This quantum tunneling process is perfectly suited for a specific and crucial type of reaction, hydrogenation. On the surfaces of interstellar dust grains, you might find unsaturated molecules, carbon chains or rings that are missing hydrogen atoms, making them highly reactive. In the cold, a regular collision might not provide enough energy for a hydrogen atom to attach, but through tunneling, the hydrogen atom can effectively teleport through the energy barrier and lock into place. One by one, over immense timescales, hydrogen atoms can tunnel their way onto these carbon skeletons, building them up into more stable and saturated forms. This slow, patient addition is the first step toward real complexity. And over millions of years, this process doesn't stop with simple hydrogenation. The cold trap allows for the gradual buildup of truly massive molecules. Simple carbon chains can link together, forming ring-like structures. These rings can then fuse with other rings, creating sprawling, chicken wire-like molecules known as polycyclic aromatic hydrocarbons, or PAHs. Astronomers have detected the spectral signatures of PAHs throughout our galaxy. They are incredibly abundant. Think of them as the fundamental soot of the universe, the basic graphene-like sheets from which even more complex organics can be built. Shielded within the icy mantles of dust grains, these PAHs can be further processed by cosmic rays and ultraviolet light, acquiring side groups of oxygen, nitrogen, and other atoms, transforming them into the potential precursors for molecules of biological significance. The final act in this cold cosmic recipe is delivery. When a molecular cloud eventually collapses to form a new star and its surrounding planetary system, all these complex organic ices coating the dust grains don't just vanish. They are incorporated directly into the building blocks of that system, the comets, the asteroids, and the planetesimals. The dust grains themselves stick together, forming larger and larger bodies, all carrying their precious cargo of pre-formed organic material. This means that from the very first moment a planet like Earth begins to coalesce, it is already being seeded with a rich inventory of complex molecules, forged in the quiet, cold depths of interstellar space. This theory suggests that the ingredients for life are not a rare planetary exclusive, but a universal commonplace, a natural byproduct of the patient, quantum-driven chemistry that occurs in the frozen darkness between the stars. But from the quiet, quantum-driven chemistry of cold molecular clouds, we now turn to a theory that is its polar opposite in almost every way. If the previous idea was a patient, slow-cooked recipe, then this one is a cosmic pressure cooker of unimaginable violence. It's the provocative notion that the very events we see as ultimate destruction, the cataclysmic deaths of massive stars in supernova explosions, could have been one of the universe's most prolific factories for the first complex molecules. This is the theory of shock synthesis, where chaos and ruin give birth to chemical creation. To grasp how this could possibly work, we need to reframe our understanding of these titanic events. A supernova is not just an explosion, it is the single most energetic phenomenon in the modern universe, briefly outshining an entire galaxy. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses in less than a second, rebounding in a shockwave of unbelievable power that blasts the star's outer layers into space at speeds approaching a significant fraction of the speed of light. This shockwave is the key. It's a wall of pure energy, compressing and heating the surrounding interstellar gas to temperatures of millions of degrees and pressures that defy comprehension. In this maelstrom, any pre-existing simple molecules would be instantly torn apart into a plasma of bare atomic nuclei and electrons. It seems, at first glance, like the last place you would look for the delicate architecture of complex organics. Yet, it is in the aftermath of this fury that the magic happens. As the supernova remnant expands outwards, it doesn't do so uniformly. It creates a complex shell structure, and the leading edge of this shell plows into the colder, denser interstellar medium like a cosmic snowplow. This is where conditions become strangely perfect for chemistry. The gas immediately behind this shock front is incredibly hot and dense, but as it expands, it does so rapidly, and rapid expansion means rapid cooling. This creates a fleeting but critical window of opportunity. The temperature and pressure drop precipitously over a very short distance and timescale. It's within this turbulent cooling zone that atoms, freshly liberated by the explosion's heat, suddenly find themselves in an environment where they can recombine. But they don't just gently drift back together, they are forced. The rapidly dropping temperature and immense pressure act like a chemical vise, squeezing atoms into close proximity and giving them no choice but to form bonds. It's a classic case of brute force overcoming energy barriers. In the laboratory, we see a similar principle at work in shock tubes, where a controlled explosion sends a shock wave through a gas mixture, and scientists observe the formation of new molecules in the cooling aftermath. On a cosmic scale, the supernova provides the ultimate shock tube experiment. Carbon, oxygen, nitrogen, and silicon atoms forged in the heart of the dying star itself, and now scattered by the blast are slammed together in this chaotic environment. They can form not just simple carbon monoxide or silicon oxide, but under these extreme conditions, they can link into more resilient ring structures and chains. The evidence for this destructive creativity isn't just theoretical. When astronomers point their telescopes at the expanding debris clouds of supernova remnants, like the famous Cassiopeia A, they do indeed detect the spectral signatures of a variety of molecules, including silicon monoxide and even more complex molecules like formilium. More tellingly, they find copious amounts of cosmic dust, including silicates and carbonaceous grains, condensing right there in the cooling ejecta. This tells us that the universe is capable of forging the very seeds of future planets and the surfaces upon which more chemistry can occur in the fires of stellar death. The supernova doesn't just create complex molecules, it creates the dust grains that will later drift into molecular clouds, becoming the catalytic platforms for the next generation of even more intricate chemistry, effectively seeding the galaxy with the raw materials for life. This creative destruction isn't limited to stellar deaths. A similar, though less extreme, process is thought to occur at the other end of the stellar life cycle during birth. The formation of a young star is a violent affair. As a protostar collapses under its own gravity, it doesn't do so peacefully. It often ejects powerful, focused jets of material from its poles, moving at supersonic speeds. These jets slam into the surrounding gas of the natal cloud, creating powerful shockwaves of their own. These shocks can compress and heat pockets of the cloud, creating localized hotspots where molecule formation can be jump-started. In this way, the tumultuous birth cries of a star can also act as a catalyst, churning the primordial soup of its nursery and forcing simple ingredients to combine into more complex forms. This theory paints a picture of a dynamic, even violent, universe where the greatest acts of creation are intimately linked with cycles of destruction, suggesting that the path to complexity was not a gentle one, but was forged in the most extreme crucibles the cosmos has to offer. Yet, for all the creative power of stellar explosions and planetary chemistry, there is a theory that takes a dramatically different approach. It sidesteps the question of how complexity began on Earth entirely by proposing that it didn't. This is the panspermia hypothesis, the captivating idea that the seeds of life, or at the very least its most complex molecular precursors, are not native to our planet but are universal travelers, scattered across the galaxy like cosmic dandelion seeds. In this view, Earth was not a solitary laboratory, but a fertile plot of land in a vast, already seeded garden. The most plausible version of this idea is known as lithopanspermia, or rocky panspermia. The scenario it paints is both violent and strangely poetic. Imagine a world, perhaps an early Mars when it was warmer and wetter, or a moon like Europa with its subsurface ocean. On this distant body, the processes of prebiotic chemistry have advanced, leading to the formation of robust organic molecules or even primitive, single-celled organisms. Then catastrophe strikes. A massive asteroid or comet slams into the planet's surface. The impact is so tremendous that it blasts fragments of the planet's crust, containing these biological passengers, out into space with enough velocity to escape the world's gravity. These fragments become meteoroids, chunks of rock adrift in the solar system. The journey through interplanetary space is, of course, incredibly hazardous. The travelers are exposed to the vacuum of space, intense cosmic radiation, and wild temperature fluctuations. For any fragile life form, it seems like a death sentence. However, research has shown that certain types of extremophile bacteria, like Deinococcus radiodurans, can enter a state of suspended animation and survive astonishing levels of radiation and cold when buried deep within a rock. The rock itself acts as a natural spaceship, shielding its microscopic cargo from the worst of the space environment. This journey isn't a quick trip. It could last for millions of years as the rock tumbles through the solar system, a dormant speck on an epic voyage. The final critical step is arrival. Through gravitational interactions, some of these meteoroids will eventually cross paths with another planet. If one were to be captured by Earth's gravity and plunged through the atmosphere, the final challenge would be surviving the fiery descent. But again, nature provides a possible solution. Smaller rocks can be decelerated high in the atmosphere, experiencing less intense heating, while larger rocks can have their outer layers ablate away, acting as a heat shield that protects a cool interior. We know this process works because we have a library of evidence, meteorites that have fallen to Earth. We've identified dozens of meteorites that originated from Mars, blasted off its surface by ancient impacts. While we haven't found definitive proof of life within them, we have detected complex organic molecules. This proves that the physical mechanism for transferring material between worlds is not only possible but has actually happened. The panspermia hypothesis transforms the entire solar system into a single, interconnected biochemical system, where planets are not isolated islands but part of an archipelago, potentially sharing the raw materials of life. It is crucial to understand what panspermia does and does not explain. This theory does not solve the ultimate mystery of abiogenesis, how life arose from non-living matter. Instead, it simply moves the goalposts, pushing that profound event to another time and another place. If true, it would mean that the origin of life is an even more universal phenomenon than we thought, but its specific solution remains hidden on some distant, unknown world. The great strength of the panspermia idea is that it dramatically expands the potential time frame and environment for life to begin. If life can travel between worlds, then it could have started billions of years before Earth even formed, perhaps around one of the universe's very first stars. This would grant evolution an almost unimaginable head start. While still a speculative and challenging theory to prove, panspermia offers a grand, interstellar perspective on our origins, suggesting that we may all be citizens of a much larger cosmic community, our biological heritage written in the stars. While the sun's ultraviolet light provided a steady, planet-wide drizzle of organic molecules, the early Earth's atmosphere was also punctuated by moments of far more intense, localized energy. This brings us to a theory that focuses on a specific and spectacular natural phenomenon, the role of lightning and electric discharge. If ultraviolet radiation was the slow cooker of atmospheric chemistry, then lightning was the cosmic blowtorch, a source of such concentrated power that it could forge complex molecules in an instant. The process begins with the raw physics of a lightning strike. On the young Earth, violent thunderstorms would have been incredibly common, fueled by intense heat from a still cooling planet and constant volcanic activity. Within these towering clouds, powerful updrafts would separate electrical charges, building up a tremendous potential difference between the cloud and the ground, or between different parts of the cloud itself. When this difference becomes too great to sustain, the atmosphere, normally an insulator, catastrophically breaks down. A blinding channel of plasma, a superheated gas of ions and free electrons, rips through the air. This is a lightning bolt, and for a fraction of a second, the temperature within that narrow channel soars to around 30,000 degrees Celsius, hotter than the surface of the sun. This isn't just heat, it's a pulse of pure, concentrated energy that fundamentally transforms the matter in its path. When this immense energy slams into the simple molecules of the primitive atmosphere, methane, ammonia, water vapor, and nitrogen, the effect is devastatingly simple. The violent collisions with electrons and the intense thermal energy literally tear these stable molecules apart. Their chemical bonds are shattered, reducing them to a soup of their atomic components, and more importantly, a shower of highly reactive fragments known as radicals and ions. A methane molecule might be broken into a methyl radical and a hydrogen atom, an ammonia molecule into an amino radical. These fragments carry an unpaired electron, making them desperate to find a partner and form a new, stable bond. For a fleeting moment, the lightning channel is a chaotic maelstrom of broken pieces. The true magic, however, happens not in the heart of the strike, but in its immediate aftermath. As the brilliant flash subsides, the plasma channel begins to cool with astonishing rapidity. The surrounding cold air rushes in and the temperature plummets. It is within this brief window of rapid cooling that the chaotic soup of radicals has its chance to reassemble. As they collide with each other in the dense, post-strike environment, they recombine. But they don't just reform the original simple gases. The recombination is a random process, and by pure chance, new and more interesting molecular architectures emerge. The carbon atoms from methane can link with nitrogen atoms from ammonia, potentially forming hydrogen cyanide, a crucial precursor to amino acids and nucleobases. Oxygen from water vapor can combine with carbon and hydrogen to create formaldehyde. The lightning bolt acts as a cosmic blender, breaking the ingredients down and then allowing them to snap back together in novel, more complex configurations. The most famous validation of this idea is, of course, the groundbreaking Miller-Urey experiment from 1953. While we've mentioned it before, its specific use of a spark discharge is a direct laboratory simulation of this very theory. Stanley Miller and Harold Urey didn't use a gentle heat source or ultraviolet lamps in their first iconic experiment. They used a continuous electrical spark between two electrodes to simulate lightning arcing through their miniature model atmosphere. The stunning success of their experiment, producing a rich mixture of amino acids and other organics in just a week, provided powerful, tangible proof that lightning could indeed be a formidable engine for prebiotic synthesis. It demonstrated that the incredible energy of a lightning strike wasn't just destructive. It was creatively destructive, capable of jumping the high-energy barriers that prevent simple molecules from reacting under normal conditions. The power of this theory is amplified when we consider the scale. Geological evidence suggests that lightning was far more frequent on the early Earth than it is today, with some estimates suggesting there could have been multiple strikes per second somewhere on the planet. Each strike would have produced a localized pulse of newly formed organic compounds. These molecules would then have been washed out of the atmosphere by rain, creating a constant planet-wide delivery system of organic feedstock directly into the accumulating pools and oceans below. This process would have provided a concentrated supply of life's building blocks, complementing the slower, more diffuse production from ultraviolet light. The theory of electric discharge presents a compelling picture of a young Earth where the very storms that racked its skies were, in fact, unseen chemists, using colossal bolts of electricity to write the first lines of the chemical code that would one day lead to life. While lightning and ultraviolet light delivered dramatic but fleeting bursts of energy, another, far more patient power source was at work deep within the Earth itself. This theory turns our attention from the sky and the atmosphere to the very ground beneath our feet, proposing that the planet's own natural radioactivity provided a slow, steady, and incredibly reliable driver for chemistry. The first complex molecules may not have been forged in a flash, but in a gradual simmer, powered by the faint, persistent decay of elements like uranium-235 and potassium-40 embedded in the early crust. The process at the heart of this idea is called radiolysis. It works on a simple but powerful principle. As unstable radioactive elements decay, they emit radiation alpha particles, beta particles, and gamma rays. These are incredibly high-energy projectiles. When this radiation passes through a material like a pocket of water, it doesn't just warm it up gently. Instead, it acts like a microscopic bullet, blasting through the medium and smashing directly into the molecules it encounters. For a water molecule, a direct hit from this radiation is catastrophic. The immense energy transferred can rip the molecule apart, tearing it into a pair of highly reactive fragments, a positively charged hydrogen ion and a neutral hydroxyl radical. This is the lysis part of radiolysis, the breaking apart by radiation. But destruction is only the first step. The true potential of radiolysis lies in what happens next. The water pocket is now suddenly filled with these reactive fragments, all created by the steady drizzle of radiation from a nearby radioactive source. These fragments don't last long. They are desperate to regain stability by forming new bonds. They violently collide with each other and with any other molecules dissolved in the water. In the early Earth subsurface aquifers or in waterlogged porous rocks near radioactive mineral deposits, this would have included simple gases like hydrogen, carbon dioxide, and nitrogen that were seeping up from below or filtering down from above. The reactive products of water radiolyses are powerful enough to drive reactions with these simple compounds, potentially reducing carbon dioxide to formate or formaldehyde, or combining hydrogen and nitrogen to form ammonia. Over time, this constant barrage of radiation-induced reactivity could have built up a rich soup of organic precursors. What makes this theory so compelling is the timescale and the environment. Unlike a lightning strike that lasts a microsecond or a sunbeam that vanishes at night, radioactive decay is relentless. A deposit of uranium ore emits radiation continuously, 24 hours a day for millions and even billions of years. This provides a perfectly stable, long-term energy source, utterly unaffected by the chaotic and hostile conditions on the planet's surface. A water-filled fissure in a rock layer above a radioactive deposit would have become a natural, self-contained chemistry lab operating with unwavering consistency for epochs. This stability is crucial because it allows for a process of trial and error. A complex molecule that forms by chance isn't immediately destroyed by the next UV blast or volcanic eruption. It has time to accumulate, interact with other molecules, and perhaps even participate in more complex reaction cycles. We see evidence that this process is not just theoretical. In the deep, radiation-filled waters of gold mines in South Africa, scientists have discovered unique microbial ecosystems that are completely isolated from the sun's energy. These microbes survive by chemosynthesis, deriving their energy from chemical reactions, and it is believed that the radiolytic splitting of water deep within the rock provides the initial reactive compounds that kickstart their entire food chain. This proves that radiolyses can indeed sustain complex chemistry and even biology over geological timescales. For the prebiotic Earth, this suggests that the subsurface world was not a barren wasteland, but a potentially fertile zone where the faint glow of radioactivity provided the quiet, persistent spark that allowed chemistry to gradually climb the ladder of complexity, safe from the storms raging on the surface above. From the chaotic energy of lightning strikes and the steady glow of radioactivity, we now turn to a theory that proposes an even more fundamental kind of chemistry, one rooted in the very minerals that make up our planet. This is the iron-sulfur world hypothesis, a groundbreaking idea put forward in the 1980s by the chemist Gunther Wechtersheuser. It presents a radical shift in perspective, suggesting that life didn't begin in a quiet pool of water, but on the gleaming, metallic surfaces of minerals like pyrite, also known as fool's gold. More importantly, it flips the traditional script on its head, proposing that metabolism, the process of capturing and using energy, came first, long before the intricate machinery of genetics. To understand this metabolism-first scenario, we need to step away from our usual focus on molecules like RNA and DNA. The central challenge of life's origin is energy. How did the first systems actively draw energy from their environment to build and sustain themselves? Wechtersheuser's brilliant insight was to identify a ready-made, naturally occurring power source, the formation of pyrite itself. On the early Earth, volcanic vents on the seafloor would have been spewing out hot, mineral-rich fluids containing dissolved iron and hydrogen sulfide. When these two compounds meet and react, they form iron sulfide or pyrite. This chemical reaction is exothermic, meaning it releases energy. Wechtersheuser proposed that this exothermic reaction could have served as the primary battery for the first metabolic cycles, providing a direct geochemical source of power. But where does the chemistry of life enter the picture? The theory posits that this pyrite-forming reaction didn't just release heat. It created a uniquely reactive environment right on the surface of the growing pyrite crystal. Pyrite has a positively charged surface, and this charge could have acted as a powerful attractor for negatively charged molecules. The most important of these would have been carbon dioxide, which was abundant in the early atmosphere and oceans. The idea is that carbon dioxide molecules would become stuck to the pyrite surface, held in place just as the energy from the pyrite formation was being released. This concentrated energy could then be used to drive a process called reduction, stripping oxygen atoms away from the carbon dioxide and leaving behind a reactive carbon skeleton. This carbon could then be built up step by step into more complex organic molecules. This sets the stage for a self-sustaining cycle, a primitive form of metabolism. Imagine a network of chemical reactions happening on a vast, rocky surface near a hydrothermal vent. The formation of pyrite provides the energy. That energy is used to fix carbon dioxide into simple organic acids. These newly formed organic molecules, still clinging to the pyrite surface, could then react with each other, forming longer chains and more complex structures. Crucially, the entire process is tethered to the mineral surface. This isn't a free-floating soup of chemicals. It's a highly organized, two-dimensional world where molecules are held in close proximity, dramatically increasing the likelihood of specific, productive reactions. The pyrite acts as both the engine and the scaffold. Wechtersheuser and other scientists have conducted laboratory experiments to test this idea, creating simulated vent environments with iron and hydrogen sulfide. In these conditions, they have successfully observed the formation of simple organic molecules like acetic acid from carbon dioxide, driven solely by the energy of pyrite formation. This lends significant credibility to the core concept. The iron-sulfur world paints a compelling picture of a gradual transition from geochemistry to biochemistry, where a simple, energy-releasing mineral reaction slowly evolved complexity around itself, eventually giving rise to the self-replicating molecular systems that would become life. It suggests that our most ancient metabolic pathways deep within our cells today might be evolutionary descendants of chemical reactions that once played out on the surfaces of iron sulfide rocks at the bottom of a primordial sea. But to truly appreciate the significance of these cosmic ice mantles, we need to zoom in to an almost unimaginable scale, to the surface of a single microscopic dust grain adrift in the silent, frigid void. Picture this grain not as a simple speck, but as a perfectly designed cryogenic laboratory, a natural marvel of cosmic engineering. Its journey begins when it condenses from the cooling gases of a dying star or a supernova remnant, a tiny nucleus of silicate or carbon. As it drifts into a cold molecular cloud, the real construction begins. Individual atoms and simple molecules from the surrounding gas, water vapor, carbon monoxide, carbon dioxide, ammonia, and methane slowly, gently adhere to its frigid surface. They don't bounce off, they stick, held fast by weak intermolecular forces. Over millions of years, these layers accumulate, building up a mantle of mixed ices that can be dozens or even hundreds of layers thick. This icy shell transforms the inert dust grain into a complex chemical repository, a frozen archive of the cloud's simplest ingredients. Within this icy matrix, however, a quiet revolution is brewing. The deep cold of space may seem like a state of perfect stillness, but it is constantly being probed by two powerful energy sources: cosmic rays and ultraviolet starlight. These high-energy particles and photons can penetrate deep into the ice mantle, and when they do, they deliver a concentrated burst of energy. This isn't enough to melt the ice, but it is more than enough to break the chemical bonds holding the simple molecules together. A water molecule might be shattered into a hydrogen atom and a hydroxyl radical. A molecule of methane might be torn apart. Suddenly, trapped within the rigid lattice of the ice, you have a population of incredibly reactive fragments, all itching to form new bonds. This process, known as radiolysis or photolysis, is the spark that ignites the chemistry. The genius of this icy environment is what happens next. In a gaseous cloud, these reactive fragments would simply fly apart, lost in the immense emptiness. But inside the ice mantle, they are prisoners in a microscopic cage. The frozen matrix acts as both a reactor and a prison. The radicals cannot escape, they are held in close proximity, vibrating with the energy of their creation. They drift slowly through the ice via a process called tunneling, and when two compatible radicals happen to meet, they combine instantly, forming a new, more stable molecule. This is how simplicity begets complexity. A hydrogen atom tunnels through the ice to meet a carbon monoxide molecule, forming formaldehyde. That formaldehyde might then be hit by another radical, adding a new functional group. Step by painstaking step over astronomical timescales, the ice mantle becomes a nursery for increasingly complex organic molecules, including alcohols, sugars, and even the precursors to amino acids. The cold that once seemed like a barrier to chemistry is in fact the essential ingredient that makes it possible, providing the stability needed for delicate structures to form without being immediately destroyed. The final act in this cosmic drama is one of release and delivery. This entire process, the accumulation, the irradiation, the slow chemical evolution, unfolds in the dark, cold womb of the molecular cloud. But when a region of the cloud begins to collapse under its own gravity to form a new star, everything changes. As the protostar ignites in the center, it begins to warm its surroundings. The temperature in the inner region of the now flattened protoplanetary disk begins to rise. For our dust grain with its precious organic-laden ice mantle, this warming is a transformative event. As the temperature climbs past 20 or 30 degrees above absolute zero, then 50, then 100, the ices that have been frozen solid for millions of years begin to sublimate, turning directly from solid to gas. The complex organic molecules that were forged and imprisoned within the ice are now liberated, released into the warmer, denser gas of the disk. This moment is the ultimate payoff. The organic inventory, painstakingly assembled in the deep freeze of interstellar space, is now injected directly into the environment where planets are beginning to form. These molecules become part of the raw material from which asteroids, comets, and eventually the planets themselves will coalesce. This theory provides an elegant and powerful explanation for a profound mystery. How did the building blocks of life end up on Earth? They weren't necessarily forged here. Instead, they were likely delivered as a standard part of the planetary construction kit, ingredients that were baked into the very recipe of our solar system from its earliest moments. The water in our oceans and the complex molecules that seeded our biology may have originated as thin layers of ice on dust grains smaller than a wavelength of light, processed by the faint light of distant stars, and then set free by the warmth of our own infant sun. Shifting our focus from the grand cosmic scales of supernova and interstellar clouds, we arrive at a challenge that is microscopic in size but monumental in importance: the formation of sugars. For all the talk of amino acids and nucleobases, the backbone of the RNA molecule, the supposed star of the RNA world, relies on a specific sugar called ribose. And ribose presents a paradox. It is absolutely fundamental to the structure of RNA, and therefore to one of our leading theories of life's origin. Yet it is notoriously difficult to form and even more difficult to keep stable under prebiotic conditions. How could the early Earth have produced enough of this finicky molecule to get life started? One of the most fascinating and intensely debated answers lies in a deceptively simple chemical process known as the Formose reaction. The beauty of the Formose reaction is its starting point, formaldehyde. This simple molecule, just one carbon atom, two hydrogen atoms, and an oxygen atom, is a veritable cosmic commonplace. We've detected it in molecular clouds, comets, and it would have been readily produced in the early Earth's atmosphere by the action of ultraviolet light and lightning on simpler gases. The Formose reaction begins when two molecules of formaldehyde, in the presence of a base like calcium hydroxide, which would have been available from weathered volcanic rocks, and a little bit of heat, start to link up. This initial coupling creates a two-carbon sugar called glycolaldehyde. From there, the reaction takes on a life of its own. Glycolaldehyde can react with more formaldehyde, and these new compounds can react with each other, leading to a chain of reactions that builds up sugars of various lengths. In a matter of hours, a clear solution of formaldehyde can transform into a complex, sugary syrup. But this is where the problem emerges. The Formose reaction is spectacularly unselective. It doesn't gently produce a nice, clean batch of ribose. Instead, it creates a messy, tangled web of almost every sugar imaginable. You get 3 carbon sugars, 4 carbon sugars, 5 carbon sugars like ribose and its close relative arabinose, 6 carbon sugars, and even longer chains. It's a chemical free-for-all. To make matters worse, ribose is particularly unstable in these conditions. It quickly breaks down, especially in the presence of the very same alkaline catalysts that drove its formation. The reaction mixture soon turns into a tarry, brown goo, a complex polymer that is largely useless for further biochemistry. So, while the Formose reaction elegantly demonstrates that sugar formation from simple precursors is possible, it seems to lead to a dead end, a sugary graveyard rather than a launchpad for life. Scientists, however, are not so quick to dismiss it. The central question has become, could the early Earth have provided a way to tame this chaotic reaction? Could specific environmental factors have acted as a guide, steering the process toward the production of the specific sugars needed for life? One compelling line of investigation focuses on the role of minerals. We've already seen how clay surfaces can organize nucleotides. Perhaps they could also bring order to sugar synthesis. Certain minerals, like borates, have shown a remarkable ability to influence the Formose reaction. Borate ions have a particular chemical affinity for sugars that have specific arrangements of hydroxyl groups, like ribose. In experiments, when borates are present, they effectively grab onto and stabilize ribose, shielding it from degradation and preventing it from reacting further into the tarry mess. This allows ribose to accumulate in the mixture to a much greater extent. Since boron is a naturally occurring element that would have been present in the early oceans, this provides a plausible geological scenario where a chaotic reaction could be nudged toward a biologically useful outcome. Another intriguing possibility involves a stepwise process rather than a single chaotic burst. Instead of relying on the full, untamed Formose reaction, perhaps the first steps happened in isolation. Glycolaldehyde, that initial 2-carbon sugar, is a much more stable molecule. It has been detected in interstellar space, suggesting it can form and survive in prebiotic environments. If pockets of the early ocean became enriched with glycolaldehyde and then received a steady, slow supply of formaldehyde, the formation of longer sugars might have been more controlled. Furthermore, the presence of other prebiotic molecules like phosphate might have also played a guiding role. Phosphate can react with sugars, and some scientists speculate that phosphorylating a sugar early on attaching a phosphate group might have stabilized it, effectively plucking it out of the reaction mixture and protecting it for future use in building nucleic acids. The investigation into the Formose reaction encapsulates a broader theme in origins of life research, the search for pathways from chaos to order. It demonstrates that the mere ability to form a building block is not enough. The context is everything. The reaction itself is a potent demonstration of the creative power of basic chemistry, but it likely required the specific conditions of the early Earth: the right minerals, the right pH, the right temperatures and concentrations, to become a viable stepping stone toward biology. It suggests that the emergence of life was not a single chemical miracle, but a series of interconnected processes where geology and chemistry worked in concert to filter, select, and stabilize the rare molecular gems from a vast background of chemical noise. But moving from a collection of individual amino acids to a functioning chain, a peptide, presents one of the most stubborn chemical riddles in the entire origins of life puzzle. The challenge is a classic catch-22 of prebiotic chemistry. The very same molecule that is essential for life as we know it is also the primary obstacle to forming the bonds that define it. That molecule is water. To link two amino acids together into a peptide bond, a molecule of water must be removed in a process called a dehydration synthesis. But in a water-rich environment like the primordial ocean or a shallow pond, the laws of thermodynamics overwhelmingly favor the reverse reaction hydrolysis, where water molecules constantly attack and break apart any nascent peptide bonds. It's like trying to build a Lego structure while submerged in a bathtub. The water keeps pulling the bricks apart. For decades, this water problem seemed to be an insurmountable barrier, suggesting that the open ocean could never have been the cradle for the first proteins. This is where our 15th theory offers an elegant and powerfully simple solution, one that turns a basic geological cycle into a planetary-scale engine for peptide production. The concept revolves around wet-dry cycles, a rhythmic pulsing of the environment that would have been as common on the early Earth as the tides. Imagine a volcanic coastline on the young planet, dotted with warm, shallow lagoons rich with amino acids that had rained down from the atmosphere or been delivered by comets. During the day, under a hot sun, the water in these pools would steadily evaporate. As the volume decreases, the amino acids dissolved within don't vanish. they become increasingly concentrated. What was once a dilute soup becomes a potent, briny film coating the rocks and sediments at the edge of the lagoon. The drying phase is where the critical chemistry kicks in. As the last of the water evaporates, the amino acids are no longer floating freely. They are forced into intimate contact on the surfaces of minerals. And not just any minerals, this theory points specifically to hot, volcanic rocks like fresh lava flows or heated clay. The combination of heat and concentration is transformative. The thermal energy from the sun, baked or geothermally warmed rock provides the activation energy needed to drive the dehydration reaction, pushing the amino acids to link up and release a water molecule. Crucially, with the bulk water now gone, there is far less available to immediately hydrolyze and break the new, fragile bond. The peptide chain is formed and then effectively baked into place on the mineral surface, much like food dehydrating in the sun. But the cycle isn't finished. The theory posits that the true genius of this process lies in its repetition. After the dry period, the next rain shower or high tide would flood the area again, rehydrating the newly formed peptides and washing them off the mineral surface back into the lagoon. This serves two vital purposes. First, it rescues the peptides from the intense heat and ultraviolet radiation of the dry phase, which could eventually destroy them. Second, and more importantly, it sets the stage for the next cycle. When the pool evaporates again, these slightly longer peptide chains can themselves become concentrated, and under the renewed heat, they can link to other amino acids or even to each other, growing progressively longer with each successive wet-dry pulse. Laboratory experiments have beautifully demonstrated the effectiveness of this process. When solutions of amino acids are subjected to repeated cycles of wetting and drying on surfaces like clay or lava rock, researchers observe the formation of peptide chains several units long. What's particularly compelling is that the mineral surfaces do more than just provide heat. They can also act as catalysts, their specific atomic arrangements helping to orient the amino acids in the correct way for the bond to form, increasing the efficiency and potentially favoring the formation of specific sequences. This theory elegantly bridges the gap between the random chemistry of a primordial soup and the structured world of biological polymers. It suggests that the first steps toward proteins were not a lucky, one-off event, but a predictable and relentless consequence of our planet's dynamic geology and climate, where the simple, rhythmic evaporation of water on a rocky shore could have patiently assembled the first molecular machines that would one day become the workhorses of life. Yet for all the elegant solutions to forming amino acids and sugars, another chemical hurdle looms just as large, one centered on an element that is surprisingly rare yet absolutely fundamental to life as we know it, phosphorus. If carbon is the backbone of organic molecules, then phosphorus is the dynamo, the element that provides energy and structure at the most critical levels. It forms the energetic currency of the cell in molecules like adenosine triphosphate, or ATP. It creates the sturdy backbone of DNA and RNA, linking each nucleotide into a long, stable chain. And it is a key component of the phospholipid bilayers that form the membranes of every single cell, creating the essential barrier between life and its environment. Without phosphorus, life simply wouldn't function. But this presents a profound mystery for the early Earth, because while phosphorus is a relatively common element in the cosmos, the specific, soluble form that biology needs was likely locked away and extremely difficult to access. The core of the problem is geology. On the early Earth, most phosphorus was bound up in highly insoluble minerals, the most common being a calcium phosphate mineral known as apatite. Think of apatite as a geological vault. It's a very stable, crystalline rock that strongly resists dissolving in water. For prebiotic chemistry to get its hands on phosphorus, it needed to find a key to this vault, a way to break the phosphorus free from its mineral prison and get it into a solution where it could react with other organic molecules. One of the most plausible keys is acidity. If water became sufficiently acidic, it could attack the apatite crystals, leaching the phosphate ions out into the environment. But where would this acidity come from? The answer lies in the volatile nature of the young planet. Volcanic activity would have spewed vast quantities of gases like sulfur dioxide into the atmosphere. When sulfur dioxide dissolves in water, it forms sulfurous acid, which could then fall as acid rain, slowly weathering volcanic rocks and releasing trace amounts of phosphate into pools and lakes. Another potential source could have been the organic acids themselves, like the acetic acid produced near iron-sulfur worlds, creating a feedback loop where early chemistry helps liberate the very elements it needs to advance. However, freeing the phosphate is only the first step in a much more difficult challenge. To become part of biology, phosphate must form a specific type of bond called a phosphate ester. This is the linkage that connects the phosphate group to the sugar in DNA and RNA, and it is notoriously difficult to form under mild prebiotic conditions. The reaction is another dehydration synthesis requiring the removal of a water molecule, and it is even less favorable in water than the formation of peptide bonds. Trying to form a phosphate ester in the primordial ocean would be like trying to light a match in a downpour. The surrounding water molecules constantly work to hydrolyze or break apart the bond almost as soon as it attempts to form. This has led many scientists to suspect that the phosphate esters we see in modern biology are actually highly evolved, refined versions of a much earlier and more reactive chemical system. This brings us to a fascinating and compelling alternative, the world of alternative phosphorus chemistry. What if the first life-like systems didn't use phosphate at all, but instead relied on other, more reactive phosphorus compounds that could form bonds more easily in a water-rich environment? One particularly intriguing candidate is a class of molecules called phosphonates. Phosphonates feature a direct bond between phosphorus and carbon, which is much more stable against hydrolysis than the oxygen-based linkage in phosphate esters. Even more tantalizing are the schrebersite minerals. Schrebersite is an iron-nickel phosphide that is commonly found in iron meteorites. When this mineral comes into contact with water, it doesn't just slowly dissolve. It undergoes a vigorous reaction, releasing a variety of reactive phosphorus species, including a compound called phosphite. Phosphite is a more reduced form of phosphorus, meaning it has more electrons, and it is far more reactive than phosphate. In laboratory experiments, phosphite has been shown to react readily with organic molecules to form phosphonate bonds under conditions that mimic the early Earth, effectively creating a potential pathway to phosphorus-containing molecules without the need for the difficult phosphate esterification. This meteoritic connection opens up a dramatic possibility. The early Earth was subjected to a heavy bombardment of meteorites, many of which were iron-rich. Each impact delivered not just a catastrophic explosion, but also a potential payload of reactive phosphorus minerals like schrebersite. When these meteorites landed in water, or when their fragments were weathered by rain, they would have created localized hotspots of phosphorus reactivity, effectively jump-starting the incorporation of this crucial element into prebiotic chemistry. This scenario elegantly combines delivery from space with favorable terrestrial chemistry, suggesting that the phosphorus problem may have been solved not by a slow, gradual process on Earth, but by a series of dramatic cosmic deliveries that provided the reactive ingredients needed to build the first energy-carrying and information-storing molecules. It paints a picture of a young planet being seeded with the chemical sparks of vitality from both its own fiery geology and the rocky debris of the early solar system. While the preceding theories have focused on the building blocks of life, the amino acids, sugars, and energy molecules, they all face a unifying challenge. Without a way to corral these components together, they would simply drift apart in the vast dilution of the primordial ocean. A protein chain or an RNA molecule, no matter how clever, is useless if it cannot be kept in close proximity to the molecules it needs to interact with. This brings us to a theory that addresses the very architecture of life itself, the lipid world hypothesis. This idea suggests that the true breakthrough toward complexity wasn't a specific molecule, but the emergence of a natural barrier, a simple bubble that could create an inside and an outside, marking the invention of the first protocell. The stars of this theory are lipid-like molecules, but they don't need to be the sophisticated phospholipids that make up modern cell membranes. The early Earth likely produced much simpler versions known as amphiphiles. The name itself tells you everything you need to know, amphi meaning both and philos meaning loving. These are molecules with a split personality. One part of the molecule is hydrophobic, it fears water and is repelled by it. This is typically a long, oily hydrocarbon tail. The other end is hydrophilic. It loves water and is attracted to it, often a charged or polar head group. This dual nature forces these molecules to behave in extraordinary ways when placed in water. The water-loving heads want to face the water, while the water-fearing tails want to hide from it. The most efficient way to satisfy both demands is for these molecules to spontaneously self-assemble into a double-layered sheet, with the tails all pointing inward, shielded from the water, and the heads facing outward on both sides. And when this sheet is large enough, it naturally curls in on itself and seals its edges, forming a perfectly enclosed spherical bubble called a vesicle. The incredible part is that this isn't a complex biological process. It's simple, inevitable physics driven by the fundamental properties of water and oil. We can see this happen in a kitchen by shaking oil and vinegar to make a temporary vinaigrette. The oil droplets are stabilized by amphiphilic molecules in the vinegar. On the early Earth, the necessary amphiphiles could have formed through several pathways. They might have been produced in the atmosphere by ultraviolet light or lightning, or synthesized on the surfaces of minerals near hydrothermal vents. Some meteorites have even been found to contain fatty acids, which are simple amphiphiles, suggesting these molecular architects could have been delivered from space. Wherever they came from, once present in the ancient seas, they would have begun spontaneously forming vesicles, creating countless tiny, microscopic enclosures. The power of these simple bubbles cannot be overstated. A vesicle acts as a fundamental concentrating mechanism. Instead of floating freely and rarely meeting amino acids, nucleotides, and other reactive molecules that happen to be inside a vesicle when it formed would now be trapped together at a much higher concentration. This dramatically increases the odds that they will collide and react, potentially forming longer chains of RNA or peptides. Furthermore, the membrane itself is not just a passive wall, it can be an active participant. If the membrane is made of the right kind of amphiphiles, it can allow small molecules like nutrients or energy sources to pass through while keeping larger, newly formed polymers trapped inside. This creates a distinct internal environment, a private laboratory where novel chemistry can unfold, protected from the disruptive currents and dilution of the outside world. Experiments have shown that these vesicles are surprisingly robust and dynamic. They can grow by incorporating new amphiphilic molecules from their environment. If they become too large, they can become unstable and divide, almost like a very primitive form of reproduction. Perhaps most fascinatingly, if you create vesicles with simple RNA strands inside, the membrane can help maintain a chemical gradient across it, a difference in ion concentration. That could have served as a primitive form of energy storage, a precursor to the complex metabolic batteries of modern cells. The lipid world hypothesis doesn't necessarily compete with the RNA world. It complements it perfectly. It provides the essential container, the physical home, where the first self-replicating RNA molecules could have been nurtured and protected, allowing them to evolve from mere chemicals into the foundation of a living system. This theory suggests that the pathway to the first cell began with a simple, spontaneous act of molecular organization, where the physics of oil and water created the first private spaces in which the chemistry of life could truly begin. While the iron-sulfur world offered a compelling vision of a metabolism powered by geological reactions, another, more intricate hypothesis suggests the first energy-harnessing systems may have had access to a far more abundant and powerful source, sunlight itself. This is the zinc world hypothesis, a fascinating variation on the metabolism first theme that proposes zinc sulfide crystals, forming in specific environments on the early Earth, acted as the universe's first solar panels, capturing light to fuel the journey from chemistry to biology. The setting for this theory is remarkably specific and hinges on a unique geological scenario. Imagine the aftermath of a massive asteroid impact on the young volcanic Earth. Such an impact would have vaporized rock, creating a plume of mineral-rich dust. Within this plume, sulfur from the impactor and zinc from the vaporized crustal rocks would have combined and condensed into microscopic crystals of zinc sulfide. Alternatively, these crystals could have precipitated directly from the superheated, mineral-laden fluids spewing from deep-sea hydrothermal vents, particularly those known as white smokers, which are cooler and richer in zinc than their black smoker cousins. These newly formed zinc sulfide crystals would then have settled, accumulating in porous, rocky deposits on the seafloor, often in shallow, sunlit waters where the Earth's crust was still thin and translucent. The magic of zinc sulfide lies in its semiconductor properties, which are strikingly similar to those found in modern solar cells. Zinc sulfide is a photocatalyst, meaning that when it absorbs light, it can use that energy to drive chemical reactions. On the early Earth, before the ozone layer formed, the sun's ultraviolet light would have penetrated much deeper into the shallow seas. This intense UV radiation would have been a destructive force for any fragile, free-floating organic molecules. But for a zinc sulfide crystal, it was a potent fuel source. When a photon of UV light strikes a zinc sulfide crystal, it knocks an electron loose from its position, creating a separation of charge and electron-hole pair. This creates a tiny, localized electric field on the crystal's surface, a burst of potential energy ready to be put to work. This is where the theory connects to the building blocks of life. The surface of the zinc sulfide crystal, now buzzing with this photoactivated energy, becomes an incredibly reactive site. Dissolved in the surrounding water were simple gases like carbon dioxide. The energized crystal surface could have provided the necessary electrons to reduce carbon dioxide, stripping away oxygen atoms and converting it into more reactive carbon-based molecules like formate or formaldehyde. This process is essentially a primitive, non-biological form of photosynthesis, using light energy to fix carbon into organic compounds. The crystalline structure of the zinc sulfide plays a crucial role beyond just capturing light. Its regular, repeating atomic lattice could have acted as a template, holding the reactant molecules in just the right orientation to make these reduction reactions more efficient and potentially even guiding the formation of specific molecular structures. What makes the zinc world hypothesis particularly compelling is how it elegantly addresses several challenges at once. It provides a continuous and vastly powerful energy source, sunlight, that is far more sustainable than the fleeting energy from a single pyrite-forming reaction. It also creates a safe haven for nascent organic molecules. Instead of forming freely in the water where UV light would destroy them, the synthesis happens directly on the crystal surface, where the molecules are immediately absorbed and protected. Furthermore, the porous, rocky deposits of zinc sulfide would have created a massive network of microscopic reaction chambers, each crystal a tiny, light-powered factory working in parallel. Over immense spans of time, this constant, sun-driven chemistry could have built up a significant and complex inventory of organic precursors, creating a fertile ground from which the first self-replicating molecular systems could eventually emerge. This theory presents a vision of a young Earth where the non-living world was already performing the fundamental trick of life, capturing external energy to build complexity long before the first true cell ever appeared. Now, as we've journeyed through these diverse theories, a consistent theme has emerged. The universe seems to possess multiple pathways to molecular complexity. But this very richness leads us to a profound and puzzling observation about life as we know it. Every living cell on Earth operates through a deeply integrated, yet strangely divided partnership. On one hand, you have proteins, the versatile workhorses that build structures and catalyze nearly every chemical reaction. On the other, you have nucleic acids like DNA and RNA, the magnificent libraries that store and transmit the instructions for making those very proteins. This elegant but intricate chicken and egg relationship is so fundamental that it's easy to take for granted. Yet, from the perspective of origins, it presents a monumental paradox. How could such a tightly interlocked system, where each half depends entirely on the other for its own existence, have possibly emerged all at once? This puzzle brings us to our 19th theory, an idea that elegantly sidesteps this conundrum by proposing that life's two great pillars had separate beginnings. This is the double origin hypothesis. The core of this theory is beautifully simple. Perhaps proteins and nucleic acids did not emerge together in a single miraculous event. Instead, they might have originated independently in completely different environments on the early Earth, each following a chemical pathway that was natural and favorable to its own structure. Imagine two distinct prebiotic worlds existing in parallel. In one world, perhaps near the mineral-rich, energetically charged surfaces of hydrothermal vents, the conditions were perfect for the formation of peptides. The heat, the catalytic properties of metal sulfides, and the flow of reactive gases could have driven the linking of amino acids into short protein-like chains, creating a world of simple metabolism and structure, a peptide world that functioned without any genetic code. Meanwhile, in another corner of the planet, a separate chemical narrative was unfolding. In sunlit tidal pools subject to wet-dry cycles, or perhaps in the atmosphere under the influence of ultraviolet light, the conditions might have been far more favorable for the assembly of nucleotides and the formation of RNA. The cyclical concentration and exposure to specific mineral catalysts like borates could have guided the formation of sugar-phosphate backbones and encouraged nucleobases to link up, giving rise to a primitive RNA world capable of both storing information and performing simple catalytic functions. For a vast stretch of time, these two systems may have evolved independently, each a testament to the universe's chemical creativity, yet completely unaware of the other. The revolutionary moment, then, was not the origin of life itself, but the origin of cooperation. The double origin hypothesis suggests that these two separate spheres of molecular complexity eventually collided. Perhaps a tide washed a population of catalytic peptides into a lagoon rich with self-replicating RNA strands, or maybe a volcanic upheaval merged a vent-based peptide system with a nucleotide-rich environment. When they met, a powerful, synergistic partnership was born. The peptides could have offered stability and enhanced catalytic power to the RNA molecules, while the RNA could have provided a means of creating more specific and efficient peptides. This merger would have been an evolutionary jackpot, creating a system so much more efficient and robust than either of its predecessors that it rapidly dominated, eventually leading to the last universal common ancestor of all life on Earth. This theory doesn't just solve the chicken and egg problem, it reframes it, suggesting that the deepest divide in biology is actually a fossilized handshake, a permanent record of the moment two separate inventions became one inseparable whole. And while the zinc world hypothesis focused on harnessing sunlight in shallow waters, a far more radical idea suggests we've been looking in the wrong direction entirely for the origins of chemistry. Instead of looking up to the sun or even across the surface of the planet, this theory proposes we need to look down, deep into the dark, hot, and immense volume of the Earth's crust itself. This is the deep, hot biosphere theory, a profoundly controversial concept championed by the brilliant and unconventional astrophysicist Thomas Gold. While Gold's primary focus was on the existence of a hidden realm of life, the implications for the origin of complex molecules are staggering. It suggests that the processes creating organic chemistry are not a surface-level phenomenon but a fundamental planetary-scale process, ongoing in the tremendous heat and pressure beneath our feet. To grasp this idea, we first have to challenge a fundamental assumption about the oil and gas that power our civilization. The standard biological theory of fossil fuels states that they are the remains of ancient life, dinosaurs, plants, and algae that were buried, cooked, and compressed over millions of years. Thomas Gold argued that this story is incomplete at best. He proposed that hydrocarbons, the chain molecules of hydrogen and carbon that include methane, propane, and petroleum, are not primarily biological in origin. Instead, he suggested that a vast amount of these compounds are abiogenic, meaning they were formed from non-living, primordial carbon that was trapped deep within the Earth during its formation. According to Gold, this primordial carbon, subjected to the intense heat and pressure of the mantle, would naturally react to form stable hydrocarbon molecules, which then slowly migrate upward through cracks and pores in the crust. The existence of such a deep, abiogenic hydrocarbon source leads directly to the theory's most captivating claim, the deep, hot biosphere. Gold reasoned that if there is a continuous, upward seepage of abiogenic methane and other energy-rich molecules from the Earth's interior, then it could support a vast ecosystem of microbial life. These microbes wouldn't rely on the sun's energy captured through photosynthesis by surface plants. Instead, they would be chemosynthetic, deriving their energy directly from chemical reactions, such as metabolizing methane or oxidizing hydrogen. This subterranean biosphere, Gold estimated, could have a total biomass exceeding that of all the life on the Earth's surface, a hidden world thriving in the absolute darkness of the crust, independent of the sun. The implications for the origin of complex molecules are profound. If Gold was even partially correct, it means that the production of organic molecules is not a rare event confined to the early Earth's surface or delivered by comets. It is a continuous planetary process. The interior of a rocky planet like Earth becomes a gigantic natural chemical reactor, constantly churning out the basic building blocks of chemistry, hydrocarbons, through purely geophysical means. This provides an alternative and potentially much more robust pathway for the emergence of complexity. Instead of a fragile surface chemistry vulnerable to asteroid impacts and ultraviolet radiation, the first steps toward life could have occurred in the stable, protected, and energy-rich environment deep underground. The deep crust offers constant temperatures, a steady supply of abiogenic feedstock, and mineral surfaces that could act as catalysts, creating ideal conditions for complex chemistry to develop over billions of years, completely isolated from the chaos of the surface. Evidence for this theory is contentious but cannot be entirely dismissed. Microbiologists have indeed discovered incredible extremophile bacteria living miles deep in gold mines and deep-sea sediments, exactly the kind of life Gold predicted. The discovery of methane on other planets and moons like Mars and Titan, where no ancient forests existed, also supports the idea that hydrocarbons can form through non-biological processes. However, the overwhelming consensus in geology is that the vast majority of Earth's economically significant hydrocarbon deposits are indeed of biological origin, as their chemical signatures often match biological precursors. The debate essentially centers on scale. While abiogenic hydrocarbons almost certainly form, are they a mere curiosity or a major planetary reservoir? Whether the deep hot biosphere theory is ultimately proven correct in its entirety is almost beside the point for our story. Its greatest contribution is the shift in perspective it forces upon us. It challenges the surface-centric view of life's origins and expands the potential habitats for chemistry across the cosmos. If the generation of complex organic molecules is an inherent property of a geologically active planet's interior, then the potential for life is not limited to a narrow, surface-based, habitable zone defined by distance from a star. It suggests that countless worlds, even rogue planets flung from their solar systems or icy moons heated by gravitational tides, could harbor deep, hot, and chemically rich environments where the universe's patient work of building complexity continues unseen in the eternal darkness. While the previous theories have explored how complex molecules might have assembled here on Earth or in the cold dark of interstellar space, we must now journey to the very forges where their most essential ingredient is created. This brings us to a theory that connects the grand cosmic cycle of life and death to the specific chemistry of life itself. It focuses on a special class of aging stars known as asymptotic giant branch or GB stars. These stellar elders are not just factories for the raw elements. They appear to be actively assembling the first links in the chain of cosmic complexity, long before planets are even a glimmer in a nebula's eye. To understand the role of an GB star, we first need to appreciate the life cycle of a star like our Sun. After spending billions of years fusing hydrogen into helium in its core, a star eventually exhausts this primary fuel. The core then contracts and heats up until it's hot enough to begin fusing helium into carbon. Meanwhile, the outer layers of the star swell dramatically, transforming it into a red giant. An GB star is what happens next in the final, turbulent stages of a low to medium mass star's life. It's a star with a complex, onion-like structure, an inert carbon core surrounded by a shell where helium is fusing, which is in turn surrounded by a shell where hydrogen is fusing. This delicate balancing act is unstable, leading to powerful pulses that drive massive stellar winds. It is this gentle, continuous exhale of the star that is so crucial. Unlike a supernova's violent explosion, a GB star sheds its outer layers in a relatively calm, though immense, wind. Over tens of thousands of years, these winds carry away a significant fraction of the star's mass, enriching the surrounding space with freshly synthesized elements. And the most important of these for our story is carbon. Deep within the star's hellish interior, the triple alpha process has been diligently fusing 3 helium nuclei into 1 carbon nucleus. This carbon is then dredged up from the core and carried to the surface by convection, where the stellar winds eventually blow it out into the galaxy. In this way, GB stars are the universe's primary producers of carbon, the fundamental atom of organic chemistry. Without these stars, the cosmos would be devoid of the central element needed for life. But the story doesn't end with the mere production of carbon atoms. The true wonder is what happens in the circumstellar envelope, the vast, expanding cloud of gas and dust that surrounds the aging star. This region is a fascinating chemical laboratory. It's much cooler than the star's surface, but it's also bathed in the star's intense infrared radiation. Here, the newly liberated carbon atoms can begin to bond with each other and with other abundant atoms, and astronomers, to their astonishment, have found that they do exactly that. When we point our radio telescopes at the envelopes of GB stars, we detect the clear spectral signatures of not just simple molecules like carbon monoxide, but of surprisingly complex carbon chains. The most compelling examples are a family of molecules known as cyanopolyenes. These are long, straight chains of carbon atoms with a hydrogen atom at one end and a cyanide group, a carbon atom triple bonded to a nitrogen atom at the other. The simplest is cyanocetylene, which has 3 carbon atoms, but astronomers have detected versions with 5, 7, and even 9 carbon atoms in these stellar environments. The discovery of these molecules was a revelation. It demonstrated that the basic architecture of organic chemistry, the linking of carbon atoms into chains and rings, is not something unique to planets. It is a universal process that begins in the winds of dying stars. The conditions in these envelopes, with their specific temperatures and densities, seem to be perfectly tailored for catalyzing the formation of these carbon skeletons. This theory presents a profound shift in perspective. It suggests that the universe is not just capable of organic chemistry, it is, in a very real sense, preconditioned for it. The laws of physics and chemistry, when applied to the material expelled by a GB stars, naturally lead to the formation of molecular structures that are direct precursors to the more complex molecules found in molecular clouds and eventually on planets. The carbon chains forged in these stellar atmospheres are the molecular seeds that will be incorporated into the next generation of stars and planets. When our own solar system formed from a cloud of gas and dust some 4.6 billion years ago, that cloud was already enriched with carbon and pre-formed organic molecules from countless generations of GB stars that lived and died before our sun was born. This means that the cosmic carbon cycle, with these stars as its engine, had already been building complexity for billions of years, setting the stage for the rapid ascent of chemistry that would occur on Earth. The path to life, it seems, was written in the stars not just metaphorically, but chemically, with the very elements of our being forged in the hearts of stars and their first complex assemblies beginning in the gentle winds of their death. Building on the idea of a metabolism-first world, we encounter a hypothesis that focuses on a specific and powerful molecular actor, one that still plays a starring role in our cells today. This is the Thioester world hypothesis, a compelling vision championed by the Nobel laureate Christian de Duve. He proposed that before the sophisticated energy currency of ATP evolved, a much simpler, more robust molecule served as the primordial power pack, the thioester. To understand its significance, we need to think about the most fundamental requirement for building complexity: activation. Simply having amino acids or other building blocks floating in a soup isn't enough. They need a jolt of energy to overcome the barrier that prevents them from linking together. In modern cells, ATP provides that jolt, but ATP is a complex molecule itself, a product of an already advanced metabolic machinery. The thioester world elegantly sidesteps this paradox by suggesting that the first activation energy came from a compound that could form much more readily on the early Earth. So what exactly is a thioester? The name gives us a clue. Thio refers to sulfur and ester describes a particular kind of chemical bond. Imagine a simple carboxylic acid, like acetic acid found in vinegar. In a thioester, the oxygen of the acid is replaced by a sulfur atom from another molecule, often a coenzyme called coenzyme in modern biochemistry. What makes this sulfur bond so special is that it is energy-rich. Forming it requires an input of energy, and when the bond is later broken, that stored energy is released and can be used to drive other reactions. This ability to capture, store, and transfer chemical energy is the very essence of metabolism, and de Duve argued that thioesters were the primordial batteries that powered the first steps toward life. The next question is crucial. How could these energy-rich molecules have formed without any biology to guide them? The answer lies in the chemistry of the early Earth, particularly environments rich in sulfur and iron, like the hydrothermal vents we've discussed. A key starting point could have been a simple reaction between a thiol, a sulfur-containing molecule, and an aldehyde or an acid. These precursors would have been available from atmospheric synthesis or vent chemistry. For instance, in the presence of a little heat or a catalytic mineral surface like iron sulfide, an acetic acid molecule could readily react with a hydrogen sulfide molecule to form an acetyl thioester. This abiotic formation isn't just theoretical, it has been demonstrated in laboratories under conditions that mimic the early Earth. The volcanic, sulfurous environments of the young planet would have been natural factories for these compounds, providing a constant geochemical supply of usable energy. Once formed, thioesters become incredibly versatile molecular tools. Their primary power lies in their ability to activate other molecules. Let's take an amino acid. On its own, it's relatively inert, but if it reacts with a thioester, it can form an aminosyl thioester. This new molecule is now primed for action like a drawn bowstring. The energy stored in the thioester bond makes the amino acid highly reactive, dramatically increasing its tendency to form a peptide bond with another amino acid. This process, called thioester-mediated peptide synthesis, provides a plausible, non-biological pathway for creating the first short protein chains. Importantly, it doesn't require the complex enzymatic machinery that cells use today. It's a direct chemical consequence of having thioesters present. This same activation principle could have applied to other building blocks like fatty acids, encouraging them to link up and form the precursors to cell membranes. The thioester world hypothesis paints a picture of a gradual, chemically inevitable ascent. It begins with simple geochemical reactions producing thioesters. These thioesters then act as catalysts for their own formation, creating a self-sustaining cycle, a primitive, non-biological metabolism. As this cycle becomes more complex, it begins to produce peptides and other polymers. Some of these peptides, by pure chance, might have had the ability to catalyze the very thioester reactions that created them, leading to a feedback loop of increasing complexity and efficiency. Over immense spans of time, this thioester-driven system could have slowly evolved, eventually inventing the more efficient and specialized energy carrier, ATP. In this view, the thioester is not a forgotten relic but the founding patriarch of our metabolic processes. The evidence is etched into the core biochemistry of every living cell. The central reaction that initiates the citric acid cycle, the fundamental metabolic pathway in all oxygen-breathing organisms, involves the formation of a molecule called acetyl coenzyme A, which is at its heart a thioester. This isn't a coincidence, it's a molecular fossil, a lasting testament to a world where chemistry first learned to harness energy, setting the stage for everything that was to come. While the grand cycles of stars provided the carbon and the energetic environments of vents offered the power, the transition to life as we know it may have hinged on the presence of a few rare but critical trace elements. This brings us to a theory that focuses not on the main actors of biology, but on the supporting cast, the elements that appear in minute quantities yet play outsized roles in guiding and stabilizing the very architecture of life. Specifically, we turn to the intriguing cases of boron and molybdenum, two elements whose unique chemistry might have been the deciding factor that steered early biochemistry down the specific path that led to us. The story of boron is intimately tied to one of the greatest challenges of the RNA world hypothesis, the instability of ribose. As we discussed earlier, the foremost reaction tends to create a messy tar of different sugars, and ribose, the essential sugar for RNA, is particularly fragile, breaking down quickly in the alkaline conditions that were likely common on the early Earth. Without a stable supply of ribose, the entire concept of a self-replicating RNA molecule becomes far less plausible. This is where boron, in the form of borate ions, enters the picture as a potential molecular guardian. Borate has a strong and specific chemical affinity for molecules that have pairs of hydroxyl groups arranged in a particular spatial configuration, a structure that ribose happens to possess. When borate binds to ribose, it doesn't just form a weak attachment, it creates a stable ring complex that effectively acts as a protective shield. This borate-ribose complex is remarkably resistant to degradation, preventing the sugar from decomposing or reacting further into that useless tarry polymer. Laboratory experiments have shown conclusively that in the presence of borate, ribose can survive for weeks or even months in conditions where it would normally vanish in a matter of hours. But for this solution to be meaningful, boron had to be available on the early Earth in a soluble, bioavailable form. This presents a fascinating geochemical puzzle. Today, boron is primarily found in dry environments, concentrated in places like the deserts of California where borax minerals are mined. How could it have been present in the primordial oceans? The answer likely lies in the intense volcanic activity of the young planet. Boron is released from the Earth's mantle through volcanic outgassing and is also found in certain clay minerals that form from the weathering of volcanic rocks. Crucially, the early Earth's atmosphere, lacking free oxygen, would have allowed boron to exist in its more soluble form. As borate-rich waters from hot springs and geothermal activity flowed into the early seas, they could have created localized environments where ribose was stabilized long enough to be incorporated into the first nucleotide chains. In this way, boron may have acted as a crucial filter, selecting for ribose over other sugars and making the emergence of an RNA-based world not just a matter of chance, but a geochemically favored outcome. The case of molybdenum is equally compelling, but for entirely different reasons. Molybdenum is a heavy metal that, in its modern biological role, sits at the heart of some of the most ancient and essential enzymes, those involved in managing the flow of nitrogen and carbon. For instance, nitrogenase, the enzyme that converts inert atmospheric nitrogen into a usable form for life, requires a molybdenum atom at its active site. The puzzle with molybdenum is one of solubility. In the presence of even tiny amounts of oxygen, molybdenum readily forms an insoluble compound called molybdate, which would have sunk to the bottom of the ocean, effectively removing it from the prebiotic chemical toolkit. On the early Earth, before photosynthesis filled the atmosphere with oxygen, this wasn't a problem. But the deeper question is, how did this relatively rare element become so central to such fundamental life processes in the first place? One provocative theory suggests that molybdenum's bioavailability was tied to a specific and dramatic change in the early Earth's environment. For the first billion years or so, the planet's oceans may have been largely devoid of oxygen but rich in dissolved iron, creating a greenish, anoxic world. In this chemical state, molybdenum would have been present in a more soluble form. However, a pivotal event known as the Great Oxidation Event, around 2.4 billion years ago, introduced oxygen into the atmosphere, which would have rapidly made molybdenum insoluble. This creates a fascinating paradox. The enzymes that require molybdenum are considered to be incredibly ancient, predating the rise of oxygen. How could they have evolved to depend on an element that was about to become scarce? This has led some scientists to propose that these enzymes originated in localized, transient environments where molybdenum remained available, such as around hydrothermal vents where oxygen levels were low. The dependence on molybdenum, therefore, might be a frozen evolutionary relic, a signature of the specific geochemical conditions that prevailed in the niche where the core metabolic pathways of life were first being forged. The presence of these trace elements in key biological functions suggests that the path life took was not arbitrary. It was deeply guided by the specific mineralogy and chemistry of our planet, a testament to the intricate dance between the non-living Earth and the emergence of biology. Now we venture into a theory that offers a grand, unifying narrative for how all these disparate pieces of chemistry might have assembled into something truly lifelike. This is the concept of molecular endosymbiosis, a powerful analogy that suggests the leap to biological complexity wasn't a single invention, but a series of mergers and acquisitions, much like the corporate takeovers that shape our economy, only on a molecular scale. It's a framework that shifts our focus from the creation of molecules to their eventual integration into a cooperative whole. The inspiration for this idea comes directly from one of the most well-established theories in modern biology, the endosymbiotic theory for the origin of complex cells. We have compelling evidence that the mitochondria powering our cells and the chloroplasts in plants were once free living bacteria. Billions of years ago, a larger, primitive cell engulfed a smaller, energy-producing bacterium. Instead of digesting it, a remarkable partnership formed. The smaller cell provided a more efficient energy source, while the larger one offered protection and nutrients. Over eons, the bacterium lost its independence, becoming a permanent, integrated organelle. This merger was so successful that it became the foundation for all complex life on Earth. The key takeaway is that a massive leap in complexity occurred not through slow, stepwise evolution of a single system, but through the sudden, cooperative fusion of two already sophisticated systems. Applying this logic to the molecular world provides a breathtakingly elegant solution to the chicken and egg paradoxes we've encountered. Imagine the early Earth not as a single primordial soup, but as a planetary-scale marketplace of molecular innovation. In one location, perhaps near a hydrothermal vent, a robust peptide-based metabolic network had evolved, good at capturing geochemical energy and converting it into useful work, but lacking any way to store instructions or replicate itself. In a sunlit tidal pool, a separate community of RNA molecules might have thrived, capable of folding into simple catalysts and even clumsy self-replication, but inefficient and fragile without a stable structure to protect them. These were independent molecular enterprises, each successful in its own niche but limited. The revolutionary moment then was a chance encounter, a molecular merger. Perhaps a vesicle formed around a cluster of metabolic peptides and by sheer luck also encapsulated a few useful RNA strands. Suddenly, these molecules were no longer competitors in a dilute ocean. They were roommates in a tiny, enclosed space. The RNA molecules, with their ability to base pair, could have begun to act as primitive templates, not for perfect replication, but for guiding the formation of peptides that were particularly helpful to the vesicle's survival. In return, the peptide metabolism provided a steady supply of activated nucleotides and energy, fueling the RNA's replication. Each system co-opted the other's strengths, creating a synergy that was far greater than the sum of its parts. What was once a loose affiliation could have, over time, become a permanent integration, with RNA genes encoding for protein enzymes and protein enzymes facilitating RNA replication. This framework transforms our view of life's origin from a single, improbable spark to a more plausible, staged process. The first stage was the abiotic synthesis of building blocks, the amino acids, nucleotides, and lipids we've discussed. The second stage was the self-organization of these blocks into primitive functional units, metabolic cycles, self-replicating RNAs, and simple membranes. The final, and perhaps most crucial, stage was the serial endosymbiosis of these units. A metabolic network merged with a replicator. That combined system then merged with a membrane that provided compartmentalization. Each merger solved a critical limitation of the previous system, creating a cascade of increasing complexity and stability. This perspective suggests that cooperation, not just competition, was the driving force behind the greatest transition in the history of our planet. The first cell may not have been a lone genius invention, but a brilliantly successful joint venture, a collaboration forged between molecules that had already spent eons learning their respective trades. But just when we think we understand the rules of chemistry, nature reveals an exception that changes everything. For decades, the water problem loomed large. How could life's essential bonds form in an environment that actively works to break them apart? The answer, according to a truly revolutionary modern theory, might have been hanging in the air all along. This is the world of aqueous microdroplet chemistry, a discovery that turns a simple mist or sea spray into a powerhouse of prebiotic synthesis. The magic lies not in the bulk properties of water that we're familiar with, but in the bizarre and extreme conditions that exist at the very boundaries of tiny water droplets. Picture an ocean wave crashing against a rocky shore, sending a fine mist of seawater into the air. Each tiny droplet in that mist is a world unto itself. While the center of the droplet might be ordinary water, its surface is a place of wild physical and chemical activity. This is the air-water interface, a frontier only a few molecules thick where water meets the atmosphere. In this incredibly thin layer, the rules are different. The water molecules are arranged in a strained, ordered structure, and there is a tremendous electric field generated by the separation of charge between the polar water molecules and the air. This creates an environment of intense reactivity that bulk water simply cannot replicate. One of the most significant effects within these microdroplets is the spontaneous creation of extreme acidity. Researchers using advanced spectroscopic techniques have made the astonishing discovery that the surface of these tiny water droplets can be extraordinarily acidic, even if the water they were made from was perfectly neutral. The pH at the surface can be 1,000,000 times more acidic than the interior. This isn't just a slight difference, it's a chasm. This extreme acidity provides a powerful driving force for chemistry, particularly for the dehydration reactions that are so crucial for building life's polymers. The high concentration of protons at the surface can catalyze the removal of a water molecule, helping to link amino acids into peptides or nucleotides into RNA chains, effectively overcoming the thermodynamic barrier that stifles these reactions in a glass of water. Furthermore, the microdroplet environment offers a form of natural concentration and confinement. As a droplet flies through the air, it is constantly evaporating. This evaporation forces the molecules dissolved within the droplet closer and closer together, dramatically increasing their chances of colliding and reacting. It's a natural version of the wet-dry cycles we discussed earlier, but compressed into a fraction of a second and occurring on a microscopic scale. The combination of extreme electric fields, radical pH gradients, and rapid evaporation creates a perfect storm of reactivity. What might take days or weeks to occur in a still beaker of water can happen in milliseconds on the surface of a flying microdroplet. The experimental evidence for this is both compelling and dramatic. In landmark studies, scientists have used electrospray techniques to create microscopic droplets containing simple amino acids like glycine. When these droplets are sprayed into a mass spectrometer, the results are astounding. Peptide bonds form almost instantaneously, creating chains of 2, 3, or even more amino acids without any added catalysts or external heat. The mere act of creating the droplet is enough to fuel the reaction. This acceleration is not minor. It can be 1,000,000-fold or more compared to the same reaction in bulk solution. This suggests that the early Earth's atmosphere, filled with sea spray from churning oceans and aerosols from geysers and volcanic eruptions, would have been a continuous planet-wide reactor. Every crashing wave and bubbling hot spring was potentially contributing a fine mist of prebiotic reactants to the air, where within each tiny droplet, the building blocks of life were being forged at an incredible rate. This theory elegantly bridges the gap between the vast dilution of the ocean and the need for concentrated, energetic conditions, proposing that the path to complexity was literally carried on the wind. The debate over where life's chemistry first ignited brings us to a fascinating geological fork in the road, one that lies at the bottom of the ocean. On one side, we have the iconic black smokers, and on the other, a more recently discovered and utterly alien landscape known as the Lost City hydrothermal field. These two environments represent fundamentally different visions of life's potential cradle, and the choice between them shapes our entire understanding of the conditions that favored life's emergence. Black smokers are the volcanoes of the deep. They form at tectonic spreading centers where seawater seeps down into the hot oceanic crust, becomes superheated, and then jets back up, saturated with dissolved minerals like iron, copper, and zinc. The result is a towering chimney, often black from precipitating metal sulfides, spewing water that can exceed 400 degrees Celsius and is highly acidic. The case for black smokers as life's nursery is a compelling one, built on the sheer, raw power of energy and catalysis. The immense temperature difference between the scalding vent fluid and the near-freezing seawater creates a massive energy gradient, a natural battery that could have been harnessed by early chemical systems. Furthermore, the porous, mineral-rich chimneys provide an enormous surface area, and the metals they contain, particularly iron and nickel sulfides, are phenomenal catalysts. These minerals can facilitate key reactions, like the reduction of carbon dioxide into organic molecules, effectively acting as a non-biological version of modern metabolic enzymes. The argument is that this high-energy, metal-rich environment provided the necessary kickstart, forcing simple chemistry to become complex chemistry through brute thermodynamic force. In stark contrast, the Lost City hydrothermal field, discovered in the year 2000 on a mountain underwater in the Atlantic Ocean, presents a completely different picture. Instead of relying on volcanic heat, Lost City vents are powered by a chemical reaction between seawater and the mantle rock called serpentinization. This process produces vents that are cooler, typically between 40 and 90 degrees Celsius, and critically, the fluid is highly alkaline, rich in hydrogen and methane, and the chimneys are not black but a stunning, ghostly white made of calcium carbonate. The arguments for Lost City as a more favorable cradle focus on gentility and stability. The lower temperatures are far more conducive to the survival of delicate organic molecules. Complex chains of RNA or peptides would be instantly destroyed in a 400-degree black smoker, but could persist and interact in the warm baths of a Lost City vent. The alkaline chemistry is also significant. The natural gradient between the alkaline vent fluid and the more neutral ocean water could have created a primitive form of energy storage, not unlike the proton gradients that power our own cells. Perhaps most importantly, the calcium carbonate structures of Lost City are incredibly porous, creating a labyrinth of interconnected microchambers. These tiny, cell-like spaces could have served as the perfect natural laboratories, compartmentalizing different experiments in prebiotic chemistry and protecting them from the diluting vastness of the open ocean. This isn't just an academic debate, it strikes at the heart of what we consider life's essential needs. Is life born from chaos and extreme energy, or does it require a protected, stable incubator? Proponents of the black smoker hypothesis point to the undeniable power of such environments and the known catalytic properties of their minerals. They argue that life is a robust process that could have emerged from the forge. Supporters of the Lost City model counter that stability is paramount, and the conditions there more closely mirror the internal environment of modern cells, particularly the energy-generating proton gradients. The discovery of Lost City forced a profound reconsideration of what a habitable environment even looks like, expanding the possibilities for life on other worlds, like Jupiter's moon Europa or Saturn's moon Enceladus, where similar serpentinization-driven vents could exist. Ultimately, the debate may not have a single winner. It's possible that both types of vents played a role, with black smokers producing basic building blocks through their intense chemistry, and Lost City-style environments providing the tranquil setting where those building blocks could finally assemble into something truly lifelike. This ongoing scientific discussion beautifully illustrates that the path to understanding our origins is as complex and branching as the chemistry itself. But among all the chemical hurdles we've explored, from forming complex chains to concentrating ingredients, one of the most subtle and profound mysteries remains almost untouched: the puzzle of handedness or chirality. Look at your own two hands. They are mirror images of each other, similar in every way, yet you cannot superimpose one perfectly onto the other. Your right glove will never fit your left hand. This same principle of handedness exists at the molecular level, And for the molecules of life, it is absolutely fundamental. Every single amino acid that builds the proteins in your body has a specific handedness. They are all left-handed. Meanwhile, the sugars that form the backbone of your DNA and RNA are all right-handed. This universal preference, known as homochirality, is a signature of life as we know it. The mystery is not just why life uses one hand, but how this incredible uniformity could have possibly emerged from a non-living world that, in all our experiments, produces a perfectly even mix of left and right-handed molecules. This initial imbalance, this breaking of the mirror, is one of the final great leaps in the story of life's origins. In the sterile environment of a chemistry lab, when you synthesize an amino acid from scratch, you always get a 50-50 racemic mixture, an equal number of left and right-handed versions. There is no inherent chemical reason for one form to be preferred over the other. Their energies are identical and they behave the same in most non-biological reactions. So, for life to have achieved its strict homochirality, some influence must have acted upon the prebiotic soup to tip the scales, to create a tiny but significant initial excess of one-handedness over the other. Once even a slight imbalance exists, it can be dramatically amplified through a process called autocatalysis, where a molecule of a certain handedness preferentially helps create more copies of itself. But the million-dollar question is, what was the original influence that gave one hand the first faint advantage? One of the most compelling theories reaches across the galaxy to the most violent and exotic objects in the universe, neutron stars. When a massive star goes supernova, its core can collapse into an incredibly dense, rapidly spinning object called a pulsar. These cosmic lighthouses emit intense beams of radiation across the electromagnetic spectrum. Crucially, this radiation can be circularly polarized. Normal light waves oscillate in many different planes, but circularly polarized light waves spiral in a specific direction, either to the left or to the right. This spinning light interacts differently with left and right-handed molecules. Think of it like a screw and a screwdriver. A right-handed screw requires a clockwise turn to drive it in. In a similar way, right-handed circularly polarized light would interact more strongly with a right-handed molecule and could even preferentially destroy its mirror image counterpart. The theory proposes that in the vast molecular clouds from which our solar system formed, clouds that were seeded with simple organic molecules, pockets of gas were illuminated by the light from a nearby neutron star. As this circularly polarized light streamed through the cloud, it would have acted as a cosmic filter, selectively breaking down one enantiomer, one-handed form of the molecules it encountered. If the light was, for example, right-handed, it would have degraded more of the left-handed amino acids, leaving behind a small but measurable excess of the right-handed form. Alternatively, it could have directly influenced the formation of the molecules, favoring the creation of one hand over the other. This would have created a localized region of space, a patch of the primordial nebula, that was already slightly biased toward a specific chirality long before the Earth even formed. This elegant idea gained support from meteoritic evidence. When scientists analyze carbon-rich meteorites like the famed Murchison meteorite, which fell in Australia in 1969, they don't find a racemic mixture of amino acids. Instead, they detect a small but consistent excess of left-handed amino acids, the very same handedness used by life on Earth. This suggests that the bias did not originate on our planet, but was already present in the raw materials from which the solar system was built. The influence of circularly polarized light from a stellar source provides a plausible, universal mechanism for how this interstellar handedness could have been imprinted. It suggests that the very orientation of our biological molecules might be a fossilized record of a long-dead star that shone its polarized light upon the nursery of our solar system billions of years ago. Of course, this cosmic explanation is not the only contender. Other theories suggest the imbalance could have arisen from more local, terrestrial sources. For instance, certain minerals with crystal structures that themselves have a handedness could have selectively absorbed one enantiomer over the other, concentrating it on their surfaces. The weak nuclear force, the fundamental force responsible for certain types of radioactive decay, has a very slight inherent chiral bias. While its effect is incredibly tiny over vast geological timescales, it could theoretically have led to a minute imbalance that was then amplified. Yet the meteorite evidence strongly points to an extraterrestrial origin, making the astronomical theories particularly powerful. The story of chirality ultimately ties the fate of our biology to the grandest astrophysical processes, suggesting that the left-handedness of our amino acids is not a mere evolutionary accident, but a direct consequence of the asymmetric physics of the cosmos itself, a subtle whisper from the stars that was then shouted aloud by the amplifying power of life. Leaving behind the stark, alien landscapes of the deep sea vents, our search for life's origins brings us back to solid ground, to a setting that is not only more familiar but also, in its own way, far more approachable. This is the prebiotic pizza hypothesis, a theory whose delightfully whimsical name belies a serious and compelling synthesis of many ideas we've already explored. It proposes that the perfect kitchen for cooking up life's first ingredients wasn't a single, exotic location, but a common and dynamic terrestrial environment, a sun-drenched volcanic field where the essential elements of chemistry were brought together in a simple, repeating cycle. Imagine the young Earth, its continent still fresh and raw, dominated by vast fields of dark, porous volcanic rock like pumice and scoria. These rocks are the crust of our prebiotic pizza. Their importance cannot be overstated. A single piece of pumice is not a solid slab. It's a foamy, microscopic labyrinth filled with an immense network of tiny pores, channels, and cavities. This creates a colossal surface area, a perfect scaffolding for molecules to gather and interact, much like the catalytic surfaces of clay or hydrothermal vent chimneys, but readily available across the landscape. Now picture a nutrient-rich source being added. This would have been water from a passing rain shower or perhaps a geyser, enriched with the simple organic molecules we've discussed, the amino acids and sugars produced by atmospheric lightning and ultraviolet light or delivered by cometary dust. As this watery solution washes over the volcanic rock, it doesn't just run off. It soaks deep into the porous matrix, carrying its molecular cargo into the countless tiny reaction chambers within the rock itself. Here, the ingredients become highly concentrated, solving the problem of dilution that would plague a vast, open ocean. Next comes the cheese and the heat, the energy and the atmosphere. During the day, the hot sun beats down on these dark rocks, warming them significantly. This solar heat provides the gentle thermal energy needed to drive dehydration reactions, encouraging those concentrated amino acids to link into peptides and nucleotides to form chains. But the energy source isn't just heat. The porous rock is also exposed directly to the atmosphere, allowing the sun's unfiltered ultraviolet light to penetrate its surface layers. This provides a second, more specific form of energy, breaking and forming bonds with pinpoint precision. The rock itself, rich in catalytic metals like iron and zinc, acts as a natural catalyst, lowering the energy barriers for these crucial reactions and potentially guiding them toward biologically relevant outcomes. The true genius of this model, however, lies in its dynamic, cyclical nature. This isn't a one-time event. The environment is subject to constant wet-dry cycles. The rock is wetted by rain, concentrating the molecules and allowing reactions to begin. Then the sun comes out, evaporating the water and baking the newly formed polymers into place on the mineral surfaces, protecting them from immediate hydrolysis. A subsequent rain would then redissolve these more complex molecules, washing them out of the rock and into a nearby pool or lagoon, where they could interact with other products from different cycles. This rhythmic pulsing between concentration and drying, between solution and solid surface, creates an evolutionary driver, allowing for a process of trial and error over countless iterations. The prebiotic pizza hypothesis doesn't require a rare, perfect set of conditions in one special place. Instead, it suggests that the entire sunlit, volcanic surface of the early Earth was a continuous, planet-wide production line, patiently and methodically assembling the pieces of the puzzle, one sunny afternoon after another, until the recipe for life was complete. But just as we've considered how the specific chemistry of our planet and the dynamics of our solar system were crucial, we must now expand our view to the grandest scale of all. Our final theory zooms out from individual molecules past stellar nurseries to encompass the entire architecture of our home galaxy. This is the concept of the galactic habitable zone, a provocative idea that suggests the very possibility of complex chemistry and life may depend on a star's cosmic address. It proposes that there is a sweet spot within a galaxy, a region where conditions are just right for planets to nurture the slow, patient accumulation of complex molecules over billions of years, and our solar system's location in the Milky Way may have been the ultimate enabling factor. The dangers of a poor galactic neighborhood become starkly clear when we consider the chaotic core of our galaxy. The central regions of the Milky Way are a dazzling but deadly environment. Stars are packed together much more densely than in our quiet suburban spiral arm. This stellar crowding leads to a dramatically higher frequency of catastrophic events. A planet forming too close to the galactic center would face a constant barrage of intense radiation from nearby massive stars and a significantly elevated risk of a nearby supernova explosion. A supernova occurring within just a few dozen light years would be an extinction-level event, not just for life but for the delicate chemical structures preceding it. The blast of gamma rays and cosmic rays would rip through planetary atmospheres, stripping them away and shredding any complex molecules that had managed to form on the surface or in the oceans. In such a hostile environment, the continuous multi-billion-year stability required for chemistry to climb the ladder to biology would be nearly impossible. The cosmic laboratory would be demolished before the experiment could ever get started. On the opposite extreme, venturing too far out into the galactic hinterlands presents a different, more subtle problem: poverty of resources. The pristine outer regions of a galaxy, in the sparse halo and the thin outer disk, are composed largely of the original hydrogen and helium from the Big Bang. They lack the rich inventory of heavier elements, the carbon, oxygen, nitrogen, and phosphorus that are the very building blocks of planets and life itself. These heavier elements, which astronomers call metals, are forged exclusively in the nuclear furnaces of stars and are scattered throughout the galaxy by supernova and stellar winds. This process of chemical enrichment happens primarily in the more densely populated inner and central regions. A star system forming far from this activity would be born from gas that is too pure, too pristine. It might have giant gas planets, but it would lack the rocky, metallic material needed to form an Earth-like planet with a diverse geology and chemistry. Without enough heavy elements, there would be no clay minerals to act as catalysts, no metal sulfides to power primitive metabolism, and certainly no rich inventory of pre-formed organic molecules delivered by comets and asteroids. The potential for complexity would be stillborn. The galactic habitable zone, then, is the ring within a spiral galaxy that lies between these two extremes. It's a region far enough from the violent galactic center to avoid constant sterilizing events, yet close enough in to have been seeded with a sufficient abundance of heavy elements from generations of earlier stars. Our own solar system resides in what is often called the galactic suburbs, about 27,000 light-years from the center, nestled within the Orion Cygnus arm. This location has afforded us a remarkable combination of safety and opportunity. We are insulated from the worst of the galactic chaos, allowing our planet to enjoy 4.5 billion years of relative stability. At the same time, we are rich in the elements of life because we formed from a cloud of gas that had been enriched by the deaths of previous stars, perhaps including the very supernova that triggered the collapse of our own solar nebula. This theory profoundly reframes our place in the universe. It suggests that the emergence of complex molecules and life is not just a matter of local planetary conditions or the properties of a star. It is a process that is deeply integrated into the structure and evolution of the galaxy itself. The Milky Way has its own life cycle, with regions that are more or less hospitable to the long-term development of complexity. Our existence may be a direct consequence of being in the right place at the right time, not just on Earth but in the galaxy. As we search for other worlds that might host life, the galactic habitable zone gives us a new map to consult, guiding our telescopes toward other stellar systems that share our fortunate cosmic address, those quiet, resource-rich neighborhoods where the universe has had the time and peace to conduct its most intricate experiments. Now we arrive at a theory that takes us to the very edge of our understanding, into a realm where the rules of the universe become strange and counterintuitive. This final idea suggests that the story of life's first molecules may be written not just in the language of chemistry, but in the even more fundamental dialect of quantum physics. The field of quantum biology is a modern frontier, revealing that processes like photosynthesis and bird navigation harness subtle quantum effects. This theory pushes that concept back to the very beginning, proposing that quantum mechanics didn't just influence early life, it may have been absolutely essential for its inception. To grasp this, we need to revisit one of the biggest challenges for prebiotic chemistry, the energy barrier. For two molecules to react, they often need a specific amount of energy to overcome a kind of chemical hill, a threshold that prevents them from spontaneously linking up. In the cold, quiet environment of a molecular cloud or a primordial pond, there often simply isn't enough thermal energy for reactants to climb this hill. Classical physics would say the reaction is impossible, but in the quantum world, particles have a fascinating property. They can behave like waves, and waves have a unique ability to tunnel through barriers, even if they don't have the classical energy to go over the top. Imagine a ball rolling towards a hill it's too slow to climb. In our everyday experience, it would just roll back. But if that ball had quantum properties, there would be a small but real probability that it would simply appear on the other side of the hill without ever going over it. This is quantum tunneling. For the first complex molecules, this quantum trick could have been a game changer. Consider the formation of molecular hydrogen in interstellar clouds. Two hydrogen atoms coming together need to shed their binding energy, but the simplest way to do this requires a third body to collide with them and carry the energy away, which is incredibly unlikely in the near vacuum of space. Quantum tunneling offers an alternative pathway. It allows the two atoms to tunnel through the energy barrier, forming a stable bond much more efficiently than classical physics would allow. This principle wouldn't be limited to hydrogen. On the surfaces of interstellar dust grains, quantum tunneling could have enabled hydrogen atoms to hop across icy mantles and attach to larger carbon chains, building up organic molecules one atom at a time in an environment where traditional reactions were frozen solid. This provides a powerful mechanism for the patient, low-temperature chemistry that we suspect occurred in the cosmic dark. But the potential quantum influence might extend far beyond simple tunneling. An even more mind-bending concept is quantum coherence. In our macroscopic world, objects have definite states and locations. In the quantum realm, a particle can exist in a superposition, meaning it can be in multiple states or places at once, at least until it's measured. This fragile state of coherence is usually destroyed by the slightest interaction with the environment, a process called decoherence. Yet, in the controlled, confined space of a potential protocell or on the structured surface of a mineral, this decoherence might have been minimized. Imagine an early pigment molecule absorbing sunlight. Instead of the energy taking a single, random path to find a reaction center, quantum coherence could have allowed it to explore all possible pathways simultaneously, essentially conducting a massively parallel search for the most efficient route to transfer that energy. This quantum walk could have dramatically increased the efficiency of the very first energy capture systems, giving them a vital edge before sophisticated enzymes evolved to do the job. This leads to the most speculative yet profoundly intriguing application: quantum information. The genetic code in DNA is a digital classical code. But the process of translating that code into a functional protein, a process that is incredibly fast and accurate, might have quantum roots. Some researchers propose that the selection of the correct amino acid by transfer RNA could involve a quantum recognition process where the molecular shapes are compared not through a slow lock and key mechanism, but through a quantum superposition that instantly finds the perfect match. If such effects were at play in the first self-replicating systems, even in a primitive form, it could explain the rapid emergence of fidelity in replication, a key hurdle in the RNA world hypothesis. The idea that the quantum world, with its blurry probabilities and interconnected states, provided the scaffolding for the crisp, reliable information storage of biology is a breathtaking possibility. It suggests that life, from its very first uncertain steps, may have been exploiting the deepest laws of the universe, weaving the weirdness of quantum mechanics into the very fabric of its existence, a partnership between the cosmos and the cell that has lasted for billions of years. And so our journey through the cosmos comes to a close, having taken us from the silent, frozen hearts of interstellar clouds to the scalding, mineral-rich cauldrons at the bottom of the sea. We have witnessed the quiet, quantum-assisted chemistry on cosmic dust grains and the violent, creative destruction of supernova. We have considered the possibility that life's ingredients were delivered by comets, forged in the sparks of lightning, or patiently assembled on the surfaces of common clay. What becomes overwhelmingly clear is that there is no single, simple answer. The path from a universe of simple atoms to one capable of building the molecules of life was not a straight line but a sprawling, messy web of possibilities, with many different processes likely working in concert across both space and time. The cold of deep space provided the stability for delicate structures to form, while the heat of planetary formation provided the energy to drive reactions forward. Geology, astronomy, and chemistry were all essential partners in this grand cosmic dance. This incredible diversity of ideas is not a sign of failure, but a testament to the vibrant and ongoing nature of scientific inquiry. The search for the universe's first complex molecules is far from over. Each time a space probe like Rosetta analyzes a comet, or a radio telescope like the James Webb peers into a distant nebula to find the spectral signature of a new organic molecule, or a lab experiment simulates a hydrothermal vent and produces a novel peptide, our understanding deepens. These discoveries don't simply prove one theory right and another wrong. They refine the entire picture, showing us how different processes could have contributed at different stages. The story is being written one discovery at a time, and we are incredibly fortunate to be living in an era where we can watch it unfold. Now we turn the question over to you. After exploring these 30 theories, from the elegant logic of the RNA world to the grand vision of the galactic habitable zone, which idea resonates most deeply with you? Does the gentle, inevitable chemistry of the lipid world with its self-assembling bubbles feel like the most natural starting point? Or are you drawn to the dramatic, cosmic perspective of panspermia, which suggests our biological heritage is written in the stars? Perhaps the iron-sulfur world, with its metabolism-first approach, strikes you as the most pragmatic solution to life's energy needs. There are no wrong answers here, only fascinating possibilities. Let us know in the comments below which theory you find most compelling and why you think it holds the key to one of the greatest mysteries of all. If you enjoyed this journey to the dawn of chemistry, Be sure to subscribe so you don't miss our next exploration into the wonders of the universe.